Here we have the grade 12 chemistry paper written in November 2022. As always, 150 marks, 3 hours. If you would like to download the paper, check the description below. Which one of the following terms describes hydrocarbons that only contain single bonds? Okay, so let's break this question down. Of course, I could just tell you the answer, but we're also going to be learning here. So hydrocarbons are the organic molecules that contain only hydrogen and carbon. There's no oxygen, there's no halogen, it's only hydrogen and carbon. That's why we call them hydrocarbons. Now, out of all of the different types of molecules, all the different homologists that we know about in grade 12, for example, we've got alkanes, we've got alkenes, then the triple bond ones, which is alkynes. Let me write that a bit better. Alkynes. Then we've got haloalkanes, alcohols, aldehydes. Now, I know that, for example, in the IEB, they sometimes don't do aldehydes and ketones, but for most of you that are watching this, you are CAPS learners, so we do have aldehydes and ketones. And then we've also got carboxylic acids, and we've got esters. And those are pretty much the 9 different homologous series that we look at in grade 12. Now, the first 3 only contain carbon and hydrogen. So those are hydrocarbons. Hydrocarbons. The rest of these, they either contain an oxygen or they contain a halogen, for example. So, okay, now it says, so now we know what hydrocarbons are. Now it says, which ones only contain single bonds? Well, we should remember that alkanes, they are the ones that have single bonds. Alkanes, alkenes, they got double bonds. And alkynes, they have triple bonds. Oh, but I see they're not even telling us about that. Oh, okay. So we need to go a little bit further into our understanding. So if we look at an alkane, a typical one would maybe look something like this. Ooh, I'm going to go make myself some coffee now, guys. Do you know I have a coffee addiction? Well, it sounds bad, but I'm not like I have maybe definitely 1 cup a day, sometimes 2. So it's nothing crazy, but the reason I say I'm addicted is like the idea of coffee. As soon as I think about it, I get like this dopamine rush. Or let's say I'm traveling and I don't know, I'm overseas somewhere, or even locally, like just the idea, like on a cold winter's day, it's really hot right now, it's summer, but just randomly, like if it's a cold winter's day, just the idea of going into like a new coffee shop and, I don't know, reading a book and drinking a cup of coffee, I don't know what it is, and listening to like French or Italian music in the background. I don't know, guys, maybe it was from my past life or something, or who knows, but that gets me going. I love that. I really do. Look, I'm not like a guy that just reads books and listens to classical music and sits in coffee shops. I've got the other side as well. I mean, I love going to night festival, like parties and stuff like that as well. I'm not just, got both parts that I'm interested in. But yeah, I just had a coffee trigger right now. Sounded quite good. So I'll go make myself some now. All right, and I don't have a coffee machine yet. I think maybe one day I would like to get one. I'm still deciding. They're quite big, so I don't want it to like take over my whole countertop. But for now, I just do like the plunger coffee, which someone showed me, I think, like 1 year out of university. I was so late onto plunger coffee. I just used to do the normal Jacobs or whatever. But now I do the whole where you put the coffee in the plunger and then you leave it for like 3 minutes and then you press the plunger down. Becoming a bit of a coffee snob, I think. But I love coffee. I really do. I've actually been doing decaf for the last 3 or 4 months. But a few days ago, I just started having normal coffee again. The reason is, it's actually quite interesting. I've actually got this really weird thing about me. Like, I've got a very busy mind. So, for example, and sometimes my mind can go down these really weird rabbit holes and like loopholes. And like, let's say, for example, I'll get this thought that maybe my heart's beating a bit faster than normal. Now, then I'll start like feeling my heart and I'll start feeling my pulse. And I don't know where this came from, guys, but I struggle with that, okay? So the other day, I was attending a night lesson because I'm busy getting my pilot's license. Not because I want to fly commercially. Ever since I was a kid, I just wanted to fly. So I'm busy getting my private pilot's license, so I can just take my mom and dad or future family. Right now I don't have any family, but future family, like a wife and kids or whatever, if that ever happens one day, who knows. Take them to, like, for a little flight around Cape Town, for example, in a small plane. So I'm not talking about doing the big planes. The work I'm doing now is what I love doing, and I'll do this forever. Anyway, so I'm busy attending this night lecture, and I hadn't had normal coffee for a very long time, okay? I'd been drinking decaf. So decaf, if you don't know what that means, it means decaffeinated. So it's got like 1% caffeine. Well, it's 99% less caffeine than normal coffee. So I became very used to that. And I didn't realize that for some people, it's not that good if you just introduce strong coffee back immediately. So I was at this night school at the flying school. It's in Stellenbosch, if any of you, for those of you that live in that area, I'm at Stellenbosch Flying School, and I ordered a coffee, and I asked them for decaf, but there was no decaf. So I said, fine, I'll just try a normal coffee. And guys, after like 30 minutes, it hit me, and I'm sitting in this lecture, and it's one of those lecturers where you got to be paying attention, because they'll suddenly look at you and they'll be like, okay, go, tell me what to do. And then you got to make sure that you were listening. Otherwise, you're going to be like, sorry, what? I blanked. So you got to be there, right? So anyways, this coffee starts entering my bloodstream, because obviously coffee, you drink it, your body digests it or whatever, and then it enters your bloodstream, and that's where you start getting the caffeine rush. But I was so used to caffeine like a couple years ago that I didn't realize how strong coffee actually is. So anyways, I've been decaf, and then I try this coffee this night, and I'm busy sitting there, and suddenly I can feel my heart beating a bit faster, and, I start going into a little bit of a like, ooh, what's going on? Suddenly my hands become a little bit more sweaty, and suddenly I'm really, like, not feeling comfortable. Like, this was the other day, this was about 3 weeks ago, and suddenly I'm really not feeling comfortable. Like, I'm feeling like, I knew it was the coffee, but I was like, wow, am I having a panic attack right now? And it got so close to the point where I nearly put my hand up to ask if I could go get some fresh air. Like, that would have been a bit embarrassing, but I nearly did that, guys. I nearly did that. So, yeah, I'm trying to think how we got into this topic. Oh, I said I was going to go have some coffee, didn't I? So anyways, so I decided from that day onwards that I can't have my life being so sensitive to coffee like that. Like, what if I get knocked over or get bumped over by a car one day, and I don't know, something silly. Like, what if the people who bumped me over, they're like, hey man, we're super sorry we bumped you over. You okay? And then let's say the ladies, there's a lady with the guy who bumped me over, and she's like, hey, we've got this coffee that we just ordered, but no one's gonna drink it. Would you like it? And then, if I say yes and whatever, then I don't want to be having panic attacks every time someone offers me coffee. Or let's say, for example, one day I go travel again, because I went to Thailand earlier this year. But let's say I go travel again, and let's say I go stay at like some family's house. I don't know, let's say some random family takes me in. Then they might offer me coffee, or like in the morning, they might wake me up and be like, hey, here's some coffee. And then obviously I'm going to drink it, but I don't want to every time do that. I want to be like, I don't want to be having panic attacks. And yeah, it probably sounds so weird, don't I? But anyway, so the reason that I'm now incorporating coffee back into my life is just to get my body used to it again. I'm not going to have a lot, but I definitely don't want to have a situation where I'm so sensitive to it that every time I have it, I'm just going to be like a nervous wreck. So that's my strategy. Now, you have to I have to apologize. Sorry, you have to forgive me. I just wasted a lot of your time, but I'm genuinely interested in sharing that story with you. And I know it has no importance, but yeah, it flowed out of that moment. And so yeah, I know that a lot of you watching this, you like literally probably having your exam in a few minutes or tomorrow, or I don't know. But I apologize about my long coffee rant. So, where were we? We said that, there was nothing related to coffee in the question. I just randomly said I'm going to go make coffee. You see how bad the addiction actually is. Like, look how long I went on about coffee for. Oh, but just quickly, I want to share another couple stories. I'm joking. I'm not going to share more stories. I know we got to get serious here. Okay, so what we said was that alkanes look like this. So this is a alkane, and then an alkene, they're the ones that have the double bond. Okay, so that's alkene, and then we've got the ones that have a triple bond. Let me rather do it like this. And these guys are called the alkynes. Now, in which of these three molecules would you not be able to add any more hydrogen? Well done if you realize that it's this one. You cannot add any more hydrogen, because how would you? I mean, if you add another one there, that's not going to work, because now this carbon has 5 things. Now, with these ones, though, we could get rid of a double bond, for example, and then that would allow us to add 2 more things. Because remember, carbon must always have 4 things around it. So this carbon at the moment has 1, 2, 3, 4, because that counts as 2. Now, if you break that one, you can just add it there, and now we still have 1, 2, 3, 4. So everything's good. But when we were looking at this one, you couldn't do that. You can't just be like, oh, wait, bro, let's do that. And then you've got 5. And then you're like, yeah, but I was making a double bond. No, now you got 6. You see? So that doesn't work. So what we did is we opened that double bond, and now all of a sudden we can add. Now you could do the same thing over here. You could take one of those away and like open up something like that, or you could even take the second one away and open up like that. So the point that I'm trying to make is that with these two, you could still add hydrogens to them. So because they are not full, they're not completely full yet, we call these unsaturated. Unsaturated. The way I like to explain unsaturated is, if you are showering, okay? Now this is getting pretty graphic, right? So you're busy showering, and then when you get out the shower, you take a towel. Now that towel is, it's dry, preferably. I'm sure we don't go into the shower. We don't shower knowing that our towel is completely wet, We usually have a dry towel, meaning that there's no water in the towel, if you can think about it like that. Then as you start drying your body, the water from your body is going to be absorbed into the towel, okay? Now, what's happening is that you are busy saturating your towel with water. Tell me about it, Kevin. Get it? Towel me about it. Yeah, so anyway, so you're busy saturating your body with water, but now if you had to take a wet towel, let's say you took a towel, dipped it in the swimming pool, and then you try to dry yourself, it wouldn't work, right? Because the towel cannot absorb any more water because it is saturated. So when something cannot absorb anything more, we call it saturated. If something can still absorb something, we call it unsaturated. So alkanes, they are saturated with hydrogen. They cannot take any more hydrogen. Whereas these ones, which I showed you when they had their double bonds and their triple bonds, they were unsaturated because they can still absorb more hydrogen. So it says here, which of the following describes hydrocarbons that contain only single bonds? Well, we know that that's the alkanes, and so we know that that would be saturated, okay? I know that was a long explanation for a multiple choice, but I guess I just wanted a bit of, what's the word? Companionship, I guess, to share my story about coffee and stuff like that, okay? Which one of the following combinations correctly indicates the strongest intermolecular forces found in ethanoic acid and methyl propanoate? Okay, so imagine this is the way I taught. Imagine I said, okay, guys, remember that it's just going to be ethanoic acid, which has hydrogen bonds, And then methyl propanoate has, remember that it's just got dipoles. Okay, so the answer is D. Okay, next question. But of course not. I would like to really go into the depth of these things so you can fully understand, so that when you get something similar or different in a test, you can work your way through it. Okay, so we've got ethanoic acid. Now, ethanoic acid is a carboxylic acid with 2 carbons, because eth means 2. So carboxylic acids, remember, they have the coo. I don't know, I think of an owl when I look at that, like cuckoo. If that's how owls even make that noise. I don't think so, but anyways, it works for me, okay? Got me through high school. So that's what we have over there. Okay, so that is ethanoic acid. Ethanoic acid. Then we've got methyl propanoate. Now you should identify that as a ester. It's going to have 3 carbons. It's going to have 4 carbons, sorry. This one is 1. And then prop means 3. So we're going to have something that looks like this. We're going to have a 1 carbon. Then we've got an oxygen. Then we're going to have 3 carbons with a double bond oxygen over there. So that's the ester part that we know about over there. And then of course we're going to have hydrogens everywhere else. Don't go put a hydrogen there, because then this carbon would have more than it would have more than 4 things around it. Okay, so these are the molecules that we now have. This is going to be methyl propanoate. So all molecules have London forces. London forces are always going to be present, okay? So if you had to take 2 ethanoic acids, they're definitely going to have London forces. And if you had to take 2 methyl propanoates, it's also going to have London forces. We cannot get around London forces. Now, this part over here, for example, is a dipole bond, or a polar bond. If you had to go look at your electronegativities, and we've spoken about this in organic chemistry already, but if you had to go look at your electronegativities, you would see that this one has a lower electronegativity than oxygen. So that means this one would be a little bit positive, this one would be a little bit negative. And so you've got this positive part. Ooh, what happened there? Ooh, no, Kev, upside down, dude. You've got this positive part and this negative part. So that's a dipole or a polar bond over there. So because of that, and you could even look at this oxygen over here, we know that this one would be negative, and so here we've got another polar section over here. So because of that area over there, which is polar, we can say that this molecule has dipole, 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 and here we've got it as well. Yes, there may be other places as well, but I'm just showing you that we can definitely see dipole, dipole. Now, this molecule over here is also going to have hydrogen bonding. When do we have hydrogen bonding? Because some of you might be like, yeah, but there's also hydrogen over here, Kev. Yep, that's true, but let's check carefully. So hydrogen bonding is when you have hydrogen plus either nitrogen, oxygen, or fluorine. Okay, let's write that a bit better. Nitrogen, oxygen, or fluorine. If you have a hydrogen bonded to any one of those, then we've got hydrogen bonding. And so if you look over here, that would be well, okay, now be careful when I say that. I'm not saying this is the hydrogen bond. I'm saying that if we had another ethanoic acid molecule, then there would be a hydrogen bond between the 2 molecules. Okay? So, but what we can say then is that there is hydrogen bonding in here, but here you won't find that. You won't find a hydrogen bonded to a nitrogen, oxygen, or fluorine. Okay, so it says here, which of the following combination indicates the strongest in ethanoic acid? Well, in ethanoic acid, it's going to be hydrogen bonding, because that is the strongest. Remember, it goes like this. London is weaker than dipole-dipole, which is weaker than hydrogen bonding. Hydrogen bonding is the strongest intermolecular force. Okay, so in ethanoic acid, it's going to be hydrogen bonding, so it could be any one of these 3. And then in this one, it is dipole-dipole, so it's this one over here, so D. a test tube contains a liquid hydrocarbon. Okay, so this is the whole bromine water thing, which we have spoken about, right? Bromine water, and when they try to identify if something is a alkane or an alkene. I hope you've watched that. It's quite important. So it says a test tube contains liquid hydrocarbon. When bromine water is added to the test tube, the mixture decolorizes immediately. That tells me it's an alkene, not an alkane. I will explain a little bit now. Which of the following combinations correctly identifies the compound? Okay, so it's definitely not these two. And what's the type of reaction? So it's definitely going to be C for those of you that already understand your work. But for those of you that maybe just want a little bit of a explanation, well, let's quickly talk about this. I'm not going to go into the depths of all the details on it because we have spoken about this many times before. But pretty much, if you have a solution over here, and then you've got a second solution over here, let's say this one is like that. Obviously, these other lines are all hydrogen bonds. Not hydrogen bonds, but hydrogen bonded to the molecule. I've got to be careful with that, don't I? Can't be saying stuff like that. So, okay, and then on this one, we're going to have some double bonded molecules, which we call alkenes. So something like that, okay? So here we have an alkane. Here we have an alkene. Okay, what they then do, okay, is imagine if you are a scientist and you need to know, let's say you've got these two solutions in front of you, but you don't know which one is, you don't know if it's a double bond and which one's an alkane, which one's an alkene. So what we do in chemistry is we use the bromine water test. Now what that does is bromine water is like an orange color, okay? Bromine, it's Br2. Br2 is a like an orange type of color. So what they do is they throw some of this bromine, or first of all, they put both of these solutions in a dark cupboard, for example. They're trying to avoid or trying to remove any light, because light is a type of energy. And with the right amount of energy, both of these reactions will actually begin to react with bromine. But if you put them both into a dark cupboard, then one of them is really going to struggle to react, while the other one can easily react, even if it is a dark cupboard. Okay, so if we now take some bromine liquid and we chuck it into this container and we chuck it into this container, what happens is that there is nothing that can happen over here. Some of you might say, yeah, but can't the bromine switch places with one of the hydrogens to become a haloalkane? That only works if we did it in a in a cupboard that, like for example, in a room that has lots of light. Then it can happen. That's the one where your reactions, you need UV and all of that. That can work. But the idea is we put this thing into a dark cupboard where there's no light, no energy, nothing like that. So nothing will happen over here. It's very difficult for something to happen over there. So this liquid will actually remain orange. Some of you might be confused about that. You're like, Kevin, but a reaction didn't happen. Exactly. Remember that this liquid is already orange. So when you add it in here, it's gonna stay orange. Why? Because nothing is going to happen. Okay, but then when you add the bromine over here, remember what I've told you before, super cringy, but these double bonds, which makes it an alkene, means that these things are very keen to react. Alkenes are very keen to react because it's so easy for them to do. All that they do is they look at this bromine and they say, hey bro, well, oh, that's actually quite funny because it's bromine, bro. I didn't even plan that. That's a good one. I can add that to my list when I go on my next date. Maybe I'll chuck that one out. Maybe the gal will find that one quite funny. I'll let you know how it goes. Quite a cracker of a joke. So as we were saying before I came up with my next pickup line, so this molecule here says, hey bro, you can come and join onto this molecule. All that needs to happen is we just need to quickly unlock this part over here, which is very easy to do. So we'll just quickly take that one away. and then we'll just open up 2 extra spaces for you. So now all of a sudden it looks like that. And then these 2 can easily just go, one of them can go there, one of them can go there. Very easy to do. To break that double bond does not require a lot of energy. As I've told you, this molecule wants to react, whereas this one, it's a bit of a loner, doesn't really want to do too much, okay? So what happens is that you throw all of these bromines into here, and they then end up going and latching themselves onto all of the different alkene molecules, and so the liquid actually loses its color because there's no longer any bromine in the liquid. That's the only reason it had that color. So this one, the whole solution will become decolorized. How do you spell that? Oh my goodness, decolorized. Whatever. There we go. So yes, it's definitely only going to work with the alkene, and that's why I've got the ene over there, okay? Now, when you take something like this and you add it onto another molecule, then that is called addition. With this question, it's quite a sneaky little one. I read through it before this, and a lot of learners would have gotten this one wrong back when this was written as an exam paper. It's quite a sneaky little catch. So have a look here. It says, which one of the following is the correct definition for the rate? Okay, now ignore these quickly. We should know that the definition of rate is change in concentration of products or reactants, be careful now, per unit time. Okay, that is what rate is. Now, here they've got the rate of change in concentration, and then here they got the rate of change per unit time. So a lot of learners would have chosen D, but it's actually not correct, because look here. Can you see I didn't add the word rate over here? But here they've got the word rate. So they're saying that okay, wait, let me show you what I mean. So change in concentration per unit time. That part there is already rate. You can see it's the same as what I've got here. That is rate. So they're actually saying the rate of the rate. That doesn't make any sense. But if you look at this one, they're using change in concentration of the product or reactant, but they never said per unit time. But because they said rate, that already means per unit time. That already means per unit time. So this one is going to be wrong because it's going to include per unit time twice, because this part already includes per unit time, and then they're saying per unit time again. So whereas this one has the per unit time as part of its definition, and then they're saying change in concentration. So it's a bit of a weird one, but the answer is C, whereas D is saying it's saying the same thing twice in a way. Consider the balanced equation for the reaction between magnesium and hydrochloric acid, okay? This is one of your typical acid-base reactions. You know all the different ones, like acid plus a metal oxide gives you salt and water. Acid plus a metal gives you salt and hydrogen. Acid plus metal hydroxide. You know, we've spoken about this before. There's lessons on this already. But here's one of the common ones. It's a metal plus an acid gives you hydrogen gas plus a salt. Okay, so now it says, which one of the following will not increase the rate? So remember, rate tells you how fast a reaction is happening. Now remember, for a reaction to happen, we have to look at the collision theory. I haven't even looked at what they're talking about here, but let's just try to remind ourselves. So, well, let's just say for a reaction to occur, molecules or atoms, whatever we have, need to collide effectively. Okay, so that's where we've looked at 3 different things. There needs to be a collision, they need to have enough energy, and they need to have the correct orientation. Now, we've said that in order for us to be able to, we can't really change the orientation. And we can't, so this one we're not going to change. You can't change that. That what that means is, how are the molecules moving around? Like, like if this molecule, let's say you've got this molecule, and then you've got this molecule, they will maybe be able to react nicely because this part here can fit into that part there, so it's gonna go nicely. But let's say this molecule was a little bit tilted, like maybe like that, then when these two molecules collide, a reaction won't happen because this part needs to fit there, but it's going to rather be hitting over there. So it wouldn't really work. That's what we talk about when we talk about orientation. And as scientists, we don't know how to change that yet. Okay? So the only things that we can do to make something faster is to use these two. Now, the way that we can do that is by using 5 different things. Okay, we can either change the concentration. If you increase concentration, you add more molecules. So that means if you have more molecules, there will be more collisions. Okay, it doesn't change the energy. So that'll change the collisions. Just giving you guys some theory as well, okay? We can change we can add a catalyst. By adding a catalyst, we lower the activation energy, so we will be influencing the energy. We can do temperature. Temperature is a powerful one. Why? Because it actually affects both of these. It increases the energy, and because the molecules are moving faster, if you increase the temperature, there's also going to be more collisions. There we go. What else? Oh, the nature. Like, for example, let's rather talk about, the surface area, whether you have a solid or you maybe have a powder. And then the last one is pressure. That's when we're talking about gases. This one we're typically talking about liquids, and then when we're talking about gases, we talk about pressure. Okay, so it says here, which of the following will not increase the rate? Well, definitely increasing concentration of HCl. We know that that's one of them. So this will definitely increase the rate. Increasing the temperature will definitely increase the rate. Now, with these two over here, this can be quite sneaky. It comes down to, we got to also look at this part here. So we know that the dilute hydrochloric acid is in excess, meaning that there is more, or it means that the magnesium is limited. So that means that when the magnesium has run out, then your reaction stops, or your reaction will begin to slow down as the amount of magnesium is running out. But there's more than enough hydrochloric acid. So if you had to go add more hydrochloric acid, that's not going to make anything faster, because the magnesium is still the one that is slowing the reaction down, because there's limited amounts of it. So if you go add more of this, it's not going to help, because you're just adding more of the thing that's already in excess. And so the answer is actually going to be A, because they said which one of the following will not increase the rate, and that's going to be adding A. You're adding more of your excess, so it's not going to help at all. So this question here, it is absolutely fine if you completely skip this one. I believe that it's a very open-ended question. I don't believe it's well designed, and I have spent a lot of time trying to go through this one and trying to think of a way of how this could work. It really is not a good question at all. I feel that some of these answers, I feel like in certain situations, all of these answers could work. You'll see why now as we go through it, but please don't try to wrap your head around this question. I feel that there's too many variables, and I just don't think it's a well thought out question. Okay, but let's try to do it. So the way we're going to do it is the answer is C, and I'm going to try to show you why A doesn't work, why B doesn't work, and why D doesn't work under most situations. But yeah, there may be a situation where A, B, and D could actually work. But let me just show you my thought process behind this. Okay, so what we're going to do is we are going to do a KC table for both scenarios, okay? So by the way, the biggest thing I want you to understand about this situation is that the KC value of R will be exactly the same as the KC value at S, okay? That is our guiding light for this question. KC at R must be the same as the KC at S. Why? Because it's the same reaction happening in the two containers, and we are at the same temperature. The KC value of a specific system stays the same at the same temperature, irrespective of how many moles of each substance we have in the container. The ratio of KC will eventually be the same for both at equilibrium. Okay, so that's something important for this argument that we are going to be making. So we're going to go do a KC table for both now. Okay, so I'm going to do the KC table over here. So we'll do it for R, and then we'll do one for S. And so the KC table is initial, change, mole at equilibrium, and then concentration at equilibrium. And we're going to assume that the volume is just, you can assume whatever you want, but I'm just going to keep it easy and make the volume 1 decimeter, and that'll be the same for both containers because they are identical. Okay. Initial, and by changing this, it's not going to make our argument different, okay? So don't worry about the fact that we're assuming a volume. Now mole equilibrium, and then concentration equilibrium. Okay, now we've got H2, I2, and 2HI, and then here we've got H2, I2, and 2HI. Okay, now initially, we've got 1, 1, 0, and 0, 0, 2. How did I get those? From the starting information over there. Okay. So we're going to try to disprove A. So A says that S will contain 1 mole of I2 at equilibrium. Okay, so let's make that happen, and then I'll show you that it can't work. Well, it can't work under most scenarios, but there might be a scenario where it does work, and that would take us a while to try to figure out. Okay, so we're going to make S have 1 mole of I2 at 1 mole over there. Okay, so we're going to make S have 1 mole at equilibrium. So there we've done that. So to get from there to there, you would have to make your change plus 1. Now that would be the same for hydrogen because they are in a 1-to-1 ratio. And then this would be minus 2. So then this would end up becoming 0, and this would end up becoming 1. So if you had to go work out your KC, it's going to be your products over your reactants. And so you're going to end up filling in a 0 over here. Even though, yeah, we haven't worked out the concentration, but it's going to be 0 divided by your volume, which is just going to be 0. So your KC value is going to be 0. But for a reversible equilibrium reaction, that can't happen. It can't happen that one of them goes down to 0 because then it's not a reversible reaction. Then it's just a single reaction. It's not a reversible. Okay? So there we've already disproved A. It can't be A. Okay, so now let's reset and then let's try disprove B. Okay, for B, they say that R will contain a larger amount of I2 at equilibrium than S. Okay, so let's make that happen. So let's make this value go down to 0.9. Or let's make it 0.8, okay? Then that means that this has to be negative 0.2. So that also means this will be negative 0.2. This will be 0.8. This will be 0.4 because it's the ratio of 2 to 1, meaning this will be 0.4. If you had to work out the concentrations, you're also going to get 0.8 because the volume is 1. Okay, now they said R will contain a larger amount of I2 than S. Okay, so then we'll make this one have a lower amount than 0.8. So let's make this one have 0.6, for example. That means that this went up by 0.6, this went up by 0.6, that means this is 0.6, and then it means that this went down by 1.2. This one's going down because in this reaction, or in S, we're starting with hydrogen iodide, and so it can only go in that direction. It can't go in this direction because there is no reactants to start with. Okay? So that means this would be 0.8. So you see, we satisfied what they said. They said R will contain a larger amount of I2. So we made R have, I2 be 0.8 over here and 0.6 over here. What we will then go and do, and then these concentrations, sorry, it's a very squashed up thing here, but okay, let's just say concentration, 0.6, 0.6, 0.8. So what we'll go do now is we will go and calculate Kc for, I'll leave that to you guys. You can go calculate Kc for this side, and you can go calculate Kc for this side, and you'll see that they're not the same. But we said that they have to be the same at the same temperature. So B also doesn't work. But some of you might be saying, Kevin, but we just chose 0.8. What if we chose another number? Wouldn't it maybe be that if we chose a certain type of number, it could maybe work out that the Kc values would be the same? And that's where I would say, I don't know. If we had enough time, we could go try multiple options and maybe we would eventually get to one. And this is why I'm also saying the question's a little bit open-ended. We cannot prove with certainty that it will be that way every time. But at least in a test, this is the kind of approach you could use, okay? You could disprove it once and assume or hope that it will hold for all values that you choose. Okay, so we've ruled out A and we've ruled out B. Let's go rule out D now, and if we can do that, then we can assume with a 90% confidence that C is the answer. And C is the answer on the memo, okay? So let's go rule out D now. Okay, so D says S will contain a larger amount of HI than R. Okay, so let's go make that happen. So let's make this value end up being 1.6, for example. That means this would have to go down by 0.4. That means these would both go up by 0.2. Okay, that means the moles at equilibrium here would be 0.2, 0.2, and then 1.6. And then if you had to work out the concentrations, you'd get 0.2, 0.2, and 1.6. Now, here, we will make the HI, let's make the HI 1.2. All that they said was that S will contain a larger amount of HI than R. So I just made this number larger than that number. That's all that they said. So that means that this would have to be positive 1.2. This would have to be negative 0.6. Negative 0.6, meaning this would be 0.4 and this would be 0.4. If you had to work out the concentrations, you would end up with that. What you would then go do, work out the Kc value for both using that expression over there, and you would find that they are not the same. Okay? They would not be the same, and so that would be a way to say that D doesn't work, because the Kc's have to be the same. As I've said, you might find a number. Remember, I chose 1.6, but you could choose a number eventually that would cause these two to have the same Kc value, and then D would actually be correct. Maybe that never will happen, but this is just my reasoning why the question is a bit weird. Okay, let's try show that C actually does work. Okay, for C, they say that they will contain the same amount of HI. Okay, great. Let's go make them have the same amount of HI. Okay, so 1 and 1. So then that means this one has gone up by 0.1, meaning that these ones will go down by 0.5, meaning that they will have 0.5 at equilibrium, and then the concentrations will be like that. Okay, then for this one, it means that this one went down by 1, meaning these would go to 0.5, 0.5, so at equilibrium that have 0.5, 0.5, and so you can see the numbers are all working out to be exactly the same. So if you had to go work out the Kc, it would be exactly the same for both, and that's good. That's good. Let's just try one more scenario though. Let's not use 1. Let's try using 0.8, and then this would also have to be 0.8. Let's see if this works out. So this would have to go up by 0.8, meaning these would have to go down by 0.4. Then this would have to be 0.6, 0.6. These would all be 0.6, 0.6, and 0.8. Okay, now this would have to be negative 1.2, meaning these would have to be, positive. Oh, it actually does work. plus 0.6. This would have to be 0.6, 0.6. These would be 0.6, 0.6, and 0.8. So if you had to go work out Kc, you would get the same for both. So the governing, or the main guiding light in this question is that Kc for R must be the same as Kc for S, and it seems that the only way we can get that to happen under most of the situations that we tried was by following C. And so the answer would have to be C. Which one of the following salts, when dissolved in water, will not change the pH? Okay, so this question is all about hydrolysis within the acids and bases section. So I'm not going to go through the entire theory of hydrolysis now. I do have videos on that where I summarize exactly what you need to know about hydrolysis, but these are all the salts. And these are the salts that you get after you do an acid-base reaction. For example, if you take, for example, let's say we have the acid H2SO4, sulfuric acid, and we react it with the base NaOH. Well, it will produce the salt Na2SO4 and water. And then for those of you that are diehard balancing fans, I would balance it just in case you don't realize that I was just doing a quick little example. And then you're like, yeah, but it's not balanced. So let me quickly balance it. I think we need a 2 over there. So that's now 6 oxygens. Yeah. Okay. So we balance, but that's not really the point of this thing. So what we look at is you look at the salt. Okay. This is a salt. Now, all that you do, hydrolysis is very easy. You just look at where, so you look at the first part and you think, where does that come from? Well, that came from NaOH. And then you look at this part and you ask yourself, where did that come from? Well, that came from H2SO4. Now, we need to know by definition that, well, not by definition, but we need to memorize certain acids and bases. We should know that this is a strong acid and this is a strong base. So because, and I've gone through this in my video on hydrolysis, so I'm not going to go into the absolute depths of knowledge right now, but if you're still unsure about hydrolysis, just check that out. But to understand or to see if hydrolysis is going to take place, you just need to look at this part and you realize that it's from a strong base and this one is from a strong acid. So when it's from something that is strong, then absolutely no hydrolysis is going to take place. Okay. If one of these was from a weak acid or a weak base, then hydrolysis will happen and the pH might change. I say might because if you've watched my video on hydrolysis, if both of these are weak, then hydrolysis does happen, but because both of them are weak, hydrolysis will happen twice and it'll cancel out to the point where the pH will remain constant. But if we get a situation like, okay, I've actually just come up with something we can do. So if you have a strong acid and a strong base, we will get no hydrolysis. Then, so pH unchanged. Actually, let's do this. Let's do this. Acid, base, will hydrolysis happen? And will the pH change? Right, so let's go situation 1, situation 2, situation 3, and situation 4. Situation 1, we use a strong acid and a strong base. Will hydrolysis happen? No. Will the pH change? No. And if we have a strong acid and a weak base, will hydrolysis happen? Yes. Now, when you have a weak base, based on that video that I've showed you, did you see that? I just said a weak base, and then I said based. Yeah, it's pretty good. So, if you look at, so if you go watch that video that I've explained about hydrolysis, you'll see that in this scenario, the acid will override, or you'll realize that the overall pH is going to be more towards the acidic side. So the pH change, will it change? Yes, and it will actually drop below 7. Okay. Now, if you have a weak acid and a strong base, will hydrolysis happen? Yes. And the pH change? Yes. And it will go above 7. So the pH will be greater than 7. So let's just go pH smaller than 7, pH bigger than 7. Then if you have a weak acid and a weak base, will hydrolysis happen? Yes, but it happens for both of these. And so will the pH change? No, because it cancels out. So the pH will remain 7, just like over here. And as I said, you've got to watch that video that I've already made. Otherwise, what I'm saying here is going to be absolute Greek. So, okay, so all we're going to do is just go look at these different salts. So if we go look at, for example, this one. Now, Na usually comes from NaOH, which you should understand, or you should remember, is a strong base. Then this one usually comes from carbonic acid, which is usually something like H2CO3. And we just need to know this, that this one is a weak acid. So here we've got we've got something weak and we've got something strong. So hydrolysis will happen and the pH will be changed, as we've seen over here. And so will the pH change? Yes. Now the question says, which of the following salts will not change the pH? Okay, so it's not that one. Now if we go to this one, the Cu part comes from, it's quite weird to have this part on the front. Usually this would be in the front. Okay, but whatever. That one's a bit of a weird one. Now I'll show you a little hack. Let's not even worry about this one, because they've written it weirdly. Let's look at this one. So this one here is from HCl, which is a strong acid by definition. NH4 is a weak base. It comes from NH3, which is a weak base. So here we've got a strong and we've got a weak. So it's this one over, well, not that one, Kev. It's this one here. So will hydrolysis happen? Yes. Will the pH change? Yes. Okay, so it's not that one for our answer. Now, if we look at this one, we've got Cl, which comes from HCl, and we've got Na, which comes from NaOH. So both of these are strong. So we've got this scenario over here. Will hydrolysis happen? Nope. And so that's our answer. So we don't really have to go look at this one. They've asked it in a really weird way. Usually this would be in the front. I don't even care about this one. We know that this is the answer, so it can't be that one. Okay. A dilute acid is titrated against a potassium hydroxide solution. At the equivalence point, the pH is 7. Which of the following combinations correctly identifies the acid and the most suitable indicator for this titration? Ugh, what an ugly question, eh? Right, so... okay, so it's actually also touching on a little bit of like hydrolysis, for example. So we know that when... and go watch my video on hydrolysis. But what we've seen is that we've got these different scenarios. 1, 2, 3, and 4. So, and this would be your acid and base. Will hydrolysis happen? And then what will happen to the pH? So if you take a strong acid and a strong base, hydrolysis will not happen and the pH will remain at 7. If you take a strong acid but a weak base, hydrolysis will happen and your pH will become less than 7. If you take a weak acid and a strong base, there will be hydrolysis and the pH will be larger than 7. And then if you take a weak acid and a weak base, hydrolysis will happen, but it happens twice, and so the pH actually cancels and neutralizes back to 7. So go check out my video on hydrolysis if what I'm saying here is completely foreign to you. I do have a video where I explain this in detail. But the main thing is that they're telling us here that at the equivalence point, the pH is 7. So we know that it cannot be scenario 2 and it cannot be scenario 3. Because in those scenarios, your pH of your final solution is not equal to 7. So let's cancel that out. And let's cancel this one out over here. Now, in chemistry, when we're doing acids and bases, we get different pH indicators, okay? Some of the more common ones are methyl orange, the good old, most difficult word in the entire universe, phenolnaphthalene. Still mentioned in some of my videos that I'm going to call my child this one day. just so that I can practice and make sure I get it perfect. Nornaphthalane. Okay, and then bromothymol blue. Right, now these pHs, these indicators, they work better. They work in different pH ranges. So methyl orange does very well in low pHs. A typical Google search, maybe your textbook is a little bit different, but typically around 2.8 to 3.8 of a pH is where methyl orange does very well. Phenol naphthalene typically changes around 8.2 up to 10, and then bromothymol blue is around 6 to 7.6. So we will choose bromothymol blue because we are capturing a pH of around 7, so that will be the one we choose. And then we said, okay, so it can't be C and it can't be A because we need to use bromothymol blue. And what we have said was that it has to be one of these two scenarios. Now, if you look at this, potassium hydroxide, that is it's a base, and it's a strong base. How do I know that? Because of what it looks like? No, because of not definition, but memory. We have to memorize the strong acids and the strong bases, unfortunately. It's just something we have to know. So if we have a strong base, then we are in this situation over here. So we need to have a strong acid. Now, this is ethanoic acid, which is weak. This is a weak acid. And this is hydrochloric acid, which is a strong acid. So D is going to be the best one. Which one of the following statements is true for an oxidizing agent? Okay, so we've looked at redox reactions. And what we know is that it is a reduction reaction. And there is also a oxidation reaction. Now we get something called an oxidizing agent, which is it's the substance which is itself reduced. Okay, let's write that nicely. Reduced, but causes another substance to be oxidized. That's the thing that used to confuse learners a lot back in grade 11 especially, is that the oxidizing agent is actually the one that is reduced, but it causes another substance to be oxidized. That's why it's the oxidizing agent, because it oxidizes something else. Now, your reducing agent is the substance that is itself oxidized, but causes another substance to be reduced. Okay, so remember, oxidizing agent gets reduced, but it causes something else to be oxidized. The reducing agent gets oxidized, but it causes something else to be reduced. Now, another thing we need to talk about is the whole idea of electrons. So in a reduction reaction, so when something is reduced, electrons are gained. And then in an oxidation reaction, electrons are lost. So when something is reduced, it gains electrons. So a reducing agent is a substance that is oxidized. So when something is oxidized, it is the oxidation reaction, so electrons are lost. So therefore, electrons are lost. And then when you have an oxidizing agent, it is the substance which is reduced. So it undergoes reduction. So electrons are gained. So it says here, which of the following statements is true of an oxidizing agent? Okay, so the oxidizing agent is this one over here. So we know that it is going to gain electrons. Okay, so we can actually just go straight to the answer A. There we go. Which one of the following metals will reduce this to this, but will not reduce that to that? Okay, so here I have table 4b. I use table 4b, and so do most of the schools in South Africa. But if you are from a school that uses 4a, that's absolutely fine. 4a is just the upside down version of 4b. That's all that it is, okay? There's nothing different on the table. It's just upside down. So that's it. Okay, so it says which of the following metals will reduce that but will not reduce that to that. Okay, so let's just go find that reaction on the table. So CD2+, okay, it's over here. So they want us to be able to take that thing and convert it to that, okay? So this reaction needs to go this way. So if you've watched any of my videos on galvanic cells, electrochemistry, you would know that for a reaction to happen spontaneously, then, okay, now it depends on how well you understand these tables, but the only substances that will allow this reaction to happen spontaneously would be the ones that are on the right-hand side and above. Ooh, how did that happen? It must be on the right-hand side and above. Okay, I'll give you an example. Let's say, for example, here they're saying zinc. So zinc probably will work, but it doesn't mean that's the answer, because we also have to look at this part over here. But let's say we look at zinc. Okay, so that zinc is over there. You mustn't circle Zn2+. They specifically talking about Zn. So then you make your reaction go that way. Now, if you, so this reaction, I know for 100% certainty, without having to go calculate the EMF, that it will work. Because I've showed you guys this before, that if you look at this arrow, if you have the one on the right-hand side above the one on the left-hand side, you see, let me try to explain again. So if you look at this arrow, and if you look at this arrow, if you have a situation where this one is below this one, then it works, because this arrow says it must be higher up and this arrow says it must be lower down. I have explained this on previous lessons, so that's why I'm going a little bit quickly now. But if we had to go a little bit more into the details now, if you wanted to, we could go and oh no, we just have that one. We could go calculate the EMF. So we know that EMF is your voltage at your cathode reaction minus your anode. Now remember, cathode is always going to be the reduction reaction, which is this one. Whenever you go from left to right like this, that's your reduction reaction. And then your anode is always where you have your oxidation, and that's the one where you go from right to left. So this is going to be your oxidation. So if you had to go work out the EMF, we would get the cathode EMF, which is negative 0.40 minus this one, which is negative 0.76. And if you had to work that out, you'd get 0.36 volts. The positive tells us that it is spontaneous, so that reaction will work. Okay? But I knew that already, and if you know your tables very well, then you should know that as soon as you have a situation like this, where you've got the one on the right-hand side higher up than the one on the left-hand side, it does work. But as soon as you have something where you've got a situation like this, where the one on the right-hand side is lower down than the one on the left-hand side, then it actually doesn't work. And if you had to go calculate the EMF, you would see it's going to give you a negative. Okay, so zinc looks like it's going to work, but let's see. They said, which one of the following metals will reduce cadmium to that? Yep, this reaction did reduce, and so we're happy over there, but will not reduce Mn2+ to Mn. Well, there's Mn2+ going to Mn. And so if we had to have a look at the zinc again, zinc is here. All of a sudden, we now have the right-hand side being lower than the left-hand side. So this reaction will not work. So our answer is actually A, because it says which one of the following metals will reduce this one. So that means everything was spontaneous over there, but will not be able to reduce this one. And that's what we're seeing over here. If we had to go work out the EMF, we should get a negative value. Let's make sure. So once again, we know that EMF is your cathode minus your anode, and your cathode is always the reduction, and your anode is always the oxidation. Now, when you go from right to left like this, that's oxidation. When you go from left to right, that is reduction. So if we had to go work out we'll take the reduction value, which is negative 1.18, and we subtract the oxidation, which is that. If you work this out, we get negative 0.42. So that negative means the reaction won't happen spontaneously. And so the answer is zinc. Zinc is able to react spontaneously with this one, but not with this one. And so guys, just remember that a very quick way to work out if a reaction will happen spontaneously is when you have a situation like this, where the one on the left is lower down than the one on the right, then it will work. Just look at the arrows. The arrows are telling you the direction that you want. So you want the one on the left to be lower down, and you want the one on the right to be higher up. So this scenario, there would be a reaction. If I gave you a situation like this, there would still be a reaction. If I gave you a situation like that, there would still be a reaction. If I gave you something like that, now all of a sudden there would not be a reaction, because the one on the left is not lower down than the one on the right. And if you had to go work out the EMF of that, you would get a negative value. Okay, so that's the quick way to do it. Obviously, if you're using table 4a, then everything's upside down, and you'd have to just make sure you interpreting that part correctly. But for this one, it's A. Here we have an organic chemistry exam question. Now remember, with organic chemistry, it is the section that I want you to have the most respect for when it comes to chemistry, because it counts the most marks by far. It's like over 30%, and it comes in 3 sections. The first one is just the general, which is like naming, drawing, all of those things. Then number 2, intermolecular forces, which is like hydrogen bonding, London forces, boiling points, all of that kind of stuff. And then number 3 is the reactions: halogenation, addition, substitution, esterification, all of those different things, okay? And they will ask it like that every single time in the exam. This would be the first kind of question, and which is like your naming and drawing kind of stuff. Then part 2, which would usually be a question 3 in an exam, would be intermolecular forces, which is typically they give you a table. And then question 4 would always be reactions. That's generally the pattern that they do. Okay, another thing is that there's going to be more questions on the next slide. So here we've got 2.3 and 2.4, 2.2 over there, and then 2.3 over there. Well, this was 2.1.3 and 2.1.4, and then 2.2 and 2.3. Okay, so let's see. First question says, write down the letters that represent 2 compounds that are isomers. Isomers, what are those again? Same molecular formula, but different structure or structural formula. So, for example, if I draw, let's say I do this, okay, and then I draw this, then both of these are alcohols. But if you had to work out, let me just quickly fill this all in. Okay, so if we had to get the molecular formula of this one, it's got 4 carbons, so that would be C4, and it's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens, and then 1 oxygen. If you had to go do the same here, you should get exactly the same. 4 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens, and 1 oxygen. So you see on paper, if you just had to look at the molecular formula, you would say that they are the same. But if you look at their structures, they're actually different. Let me just get rid of all these ugly circles. This one has the OH on carbon 2, whereas this one has the OH on carbon 1. So they're both alcohols, but their name would be different and they have slightly different properties because of that. So that is what isomers are. They are the same molecular formula, so same amount of carbons, hydrogens, oxygens, but they're a little bit different when you draw them out. Okay. So they said write down 2 organic compounds, and this is, it's also with isomers where you get the 3 different types. You get chain, position, and functional. Okay, so go watch my videos on isomers. I'm not going to go into the deep theory on all of that now. Of course, this is an exam paper, so yeah, don't have time to go do the theory for every single question. It would take us like 9 hours per exam paper. But let's try see what we can come up with here. So what you could do, if you were in an exam, you could just quickly check how many carbons are on this one. So 1, 2, 3, 4, 5, 6, 7, 8. That'll help us to quickly narrow down which ones it could be. 3, 4, 5, 6, 7. 1, 2, 3, 4. And 1, 2, 3, 4. Okay, so it could be those two. 1, 2, 3, 4. And then 1, 2, 3, 4. Okay, goodness me. Of course, they had to make our life challenging. So it can't be these two because they have 8 and 7 carbons. So we don't even have to go look at the hydrogens and the... because if the carbons aren't the same, then nothing else. I mean, it doesn't matter what happens to the rest. Okay, then let's go a little bit further now. So if we look at this one, it's got how many hydrogens? So it's got 4 carbons, and the hydrogens would be 3, 5, 7, 8. Okay. For this one, it's got 3, 5, 8. Okay. This one here has 3, 5, 7, and 8. And then this one's got 3, 5, 7, 8, 9, 10. Okay, so this one's out. It can't be this one because this one would never match with any of the others. Okay, so A's out, B's out, F is out. Okay, so now we need to go, let's go a little bit further. Let's go do the oxygen. So this one has 1 oxygen, or we can just do that. This one has 1 oxygen. This one has 2, so that one's out. Aha, so it has to be these two then. They have the exact same amount of everything. So write down the 2 organic compounds that are isomers of each other. It would be C and D. This question says, write down the type of isomers, chain, functional, or positional, identified in question 2.1.1. Okay, so let's go draw it out. I always like to draw it out. I've been doing this for so long, but I still draw it out, okay? So CH3 is going to be, so let's quickly do molecule C, and then we'll do molecule D over here. So CH3, then there's a CH2, then there's another CH2, and then there's a carbon, double bond oxygen with a hydrogen. Yes, I know that this hydrogen is going down, but it doesn't matter if I put it like that, okay? And then D is going to be CH3, and then CH2, and then this, and then there's a CH3. All right, now I've spoken about isomers before, so when it comes to chain, then it's the same amount. Oh, sorry. If it is a chain isomer, then it's different amount of carbons in the main chain. Now, when I talk about the main chain, I'm talking about the longest continuous chain. So this one has 4, and then this one has 4. So if it was a chain isomer, they would have a different amount of carbons. But these ones have the same amount of carbons, and so it's not going to be chain isomerism. Okay? Then you get functional. So that's when you have different homologous series. So that's like if you have an alcohol and an aldehyde, for example. You know the different homologous series like ketone, aldehyde, carboxylic acid, alkane, alkene, alkyne, haloalkane. If you have different ones, then that's functional isomerism. But if you look here, we've got a carbon with a double bond oxygen, and we've got a hydrogen. Oh, here we go. Hydrogen on the side. Now, what have I always said when it's on the side? This riddle drives me mad even. When the hydrogen's on the side, it's a aldehyde. Okay, Kev, you are definitely smoking some interesting stuff, my bro. And then with this one, we've got a carbon, double bond oxygen, but it's not on the side of the molecule. It's in between two carbons. So this is a ketone. So if you're an IEB student right now, you guys typically don't look at aldehydes and ketones. So this question is probably not looking normal to you, so don't worry about that. You guys, I mean, they might change it. Maybe they are busy changing it, but typically they don't do aldehydes and ketones. But the CAPS learners, which most of you watching this are CAPS learners, we obviously do aldehydes and ketones. So you see we've got two different functional groups. And so, well, we've got two different homologous series. So it's going to be functional. Okay, so moving on, this question says, write down the general formula. What is the general formula? That's when they do like the CnH2n and all of that stuff. CnH2n, CnH2n minus 2, blah, 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 blah. That is what general formula is. So it says, write down the general formula of the homologous series to which compound B. Okay, compound B has a triple bond, so you should know that that is an alkyne, and you should know that alkynes are like this. Okay, but if you were in a test and you couldn't figure it out, don't draw this one. Just go draw any alkyne, because this formula is for all alkynes. It's the general scenario. So just go draw a basic one like that. Go fill in all the hydrogens. Now there's no hydrogens over there or on those two, because then this carbon would have more than 4 and then this carbon would have more than 4. Okay, so what we can do is we can see that there are 4 carbons and there are 1, 2, 3, 4, 5, 6 hydrogens. So if in your test you're like, I can't remember, is it like this? Well, this one wouldn't make sense because it says that the hydrogen is 2 times the carbon, but that's definitely not 2 times. So it can't be that one. Then you might be like, is it this one? Well, if this is a 4, then this would be 2 times 4, which is 8, plus 2, which is 10. So that won't work. Then you might be like, is it maybe this one? Well, yes, because if this is a 4, then if you plug a 4 in over there, it's 2 times 4, which is 8, minus 2, which is 6. So it's definitely that one over there. And obviously, guys, I've made lots of videos on this already. So, yeah, this is all under general formula. Okay, now it says 2.1.4, name of the functional group. Okay, yeah, so we get different names for functional groups, like hydroxyl. We even get some weird ones like formal, carboxyl, all these weird things. Let's go see. For compound F. Okay, so for compound F, your functional group, what is a functional group? Functional group is the section or the molecules or the atoms that make that specific molecule unique. It's the part that makes it interesting, okay? And so it's not that. It's definitely this area over here. So if we had to zoom in a little bit closer, it's a CH2 with an OH attached. Okay, so the functional group is that part over there. It's the carbon with the OH. That is called a hydroxyl group. Hydroxyl. And you get different ones. You get carbonyl, carboxyl, formal. It's a weird word. I sound very Afrikaans when I say it. I'm not Afrikaans, by the way, but when I say formal, it's like, hello, bro. Yes, my name's Pieter. Ek's Pieter. My van is Baardenors. En, yes, bro, when I study physics, the carbonyl and the formal groups, it's be taking my time. So yeah, when I say formal, I sound very Afrikaans. It's like, I always find it funny, sometimes when Afrikaans people are like really being dramatic and they're like busy ranting about something, and then they just like throw in a little bit of English there. They'll be like, yes, bro, so the other day was at soos, oh my word, bro, you cannot do that. And dan was ek soos, hello, ek staan hier. And then you're like, I cannot be here. And then, yeah, I've seen some, when I was in high school and stuff, I saw some like some cat fights, I guess. And then the Afrikaans girls, they're like, I went to a school that was, I think, mostly English, probably like a 60-40, maybe a 65-35, or like a 64-36 split or whatever, between Afrikaans and English. But yeah, Afrikaans, it's funny when they're like getting really dramatic, and then they just throw in a bit of like the Afrikaans there. But yeah, anyways, I think I should move on because I don't want to get myself into any trouble. Look, I love every people, okay? Like I had a lot of Afrikaans friends when I was in high school. I had a lot of every type of demographic that you can think of. So I'm like a Trevor Noah, okay? Ja, Leandri, so die ander dag, nee, was ek soos, oh my word, you cannot stand it, girl. En dan was ek, toe hulle skel hulle vir my, en ek soos, okay, I don't know what's going on, I need to stop, I need to carry on. So, it says, name of the functional group. I'm a character, hey? Like, I'm looking at myself from the outside, and I'm like, this guy is absolutely, he's nuts, and it's me, like, I have to live with this guy. I gotta live with this Kevin, and it's me. I mean, okay, definitely, I probably need to go to, like, probably get some help here. No, I'm just joking, guys, I'm fine. So it says, name of the functional group, we already did that one, hydroxyl. Ooh, here's all the naming. Okay, now naming should be beautiful. Like, it should be an easy marks for you. I've made so many videos on this. So let's give it a go. So it says, write down the IUPAC name of compound A. Okay, so compound A. Okay, so remember, I've gone over this in details, hey guys. So step 1, let's identify the longest chain. Now, some students think that just means that. No, the longest chain is start somewhere and see how many carbons you can link without lifting up your pen. So there. Now, if you go that way, then that'll only give you 4. Then you can't go that way, or you can't go there, and then come back, because then you got to only go in one. You don't want to like go over the same carbon twice. You're going to go there. Then if you went there, that would be 1, 2, 3, 4, 5. But what if I go there? Ha, look at that. 1, 2, 3, 4, 5, 6 carbons. Okay, fantastic. Now, we got to try see, is this a alcohol, carboxylic acid, ketone, alkane, alkyne? What is it? Well, it's got this bad boy over here. So this means that this is a haloalkane. But if you've seen some of my videos, I haven't said it in. It's something that I talk about only sometimes in some videos when the situation presents itself. But I've often made fun of haloalkanes, and I've said that they are like a failure of homologous series, because when we name them, we don't try to name them closest to this part over here like we would normally do for something like this or this or this or this or this, right? With haloalkanes, we don't say, oh, wow, you're so important. We say, hey, brah, get out of our way. Like, this thing's not that important. We stick to the normal rules of alkanes, and we try to make the branch numbers as low as possible. So, if we had to start at this carbon, then your branches, where are the branches? Let's go quickly highlight all the branches. Your branches would be the parts that are sticking out, there and there. Those are your branches. So this would be carbon number 1, this would be carbon number 2. If we did it this way, this would be carbon 4, this would be carbon 5, and this would be carbon 6. So your branches would be on carbon 3 and 4. Can you see it? On 3 and 4. I know that there's 2 of them on 4, but we're just going to say 3 and 4 for now. Now, if we named it from the other side, okay, let's just write 3 and 4. If we named it from the other side, then it would be 1, 2, 3, 4, 5, 6. Now, when a situation like this happens, then we don't want to just choose any side. What we need to now do is actually realize that for the one that we have here, we've got 2 branches on number 3. Okay, so we're going to say 3 and 3. And then for the previous one, when we did that one, we had carbon 1, 2, 3, 4, 5, and 6. So on carbon 3, we only had 1 branch, but then on carbon 4, we had 2. So we had like that. So then if you add these numbers up, you would get 11. And if you add these numbers up, you would get 10. So we choose the lowest one, which is going to be the 10. This doesn't happen too many times where we have to go this deep into the analysis of it. But yeah, in this one, it's going to be that. So to get that 334, then we have to name it from this side. So 1, 2, 3, 4, 5, 6. Okay, so when we name it, the first step is to find the longest chain, which we said was 6 carbons. That's going to be hexane. When it's a haloalkane, at the ending part here, you don't put like halo. You don't say hex halo or anything. You just say hexane. And then in the front over here is the branches. So on carbon 3, we have a methyl. Then on carbon 3, we have another methyl. And then on carbon 4, we have a bromo. So we use the alphabet. So B comes before M. And so even though this one's going to have a di, we don't look at the D. We look at these letters, okay? So B will come first. So we say 4 bromo. Now I'm going to run out of space. Then we're going to say 3 and then another 3. And then we're going to say dimethyl because there's 2 of them. And so that's how you'll name that molecule. Now we're going to name compound B, which is an alkyne. Step 1, find the longest chain. So remember, that doesn't just mean doing that. I mean, it could. That might be the longest, but explore the different options. So we could go like that. That would be 1, 2, 3, 4, 5. If we go this way, 1, 2, 3, 4, 5. And if we go this way, 3, 4, 5. Okay, so any one of those will be correct. I'm just going to use the most easiest one, which is the straight line like that. Now, everything else that's sticking out is then going to be considered a branch. So there's our branches. Of course, these hydrogens, we don't count those as branches. Okay, so that's 1, 2, 3, 4, 5. So that's going to be pent. So we're going to say pent. Now, when you have a functional group like this, or a double bond, alkene, or alcohol, carboxylic acids, esters, we always name it from the side closest to the functional group. We don't try to make the branches as low as possible like we did over here. When it's normal kind of molecules, we always go from the side closest to the functional group. So even though the branches are closer to the left side, we will not name it from the left because the functional group is closer to the right. Because if I name this as carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, then I can see my functional group is starting on carbon 2. But if I started naming from the left, then this would be carbon 1, this would be carbon 2, and then your functional group would only start on carbon 3. So we will rather name it from the right-hand side, where the functional group would then start on carbon number 2. So some of you are like, but yeah, Kev, then why did we not name it closest to the functional group? Good question. And that is what I was talking about when I said that haloalkanes are like the failures of, it's an ugly word, but they are like the failures of homologous series. Their functional group is it's not taken very serious. Like this thing walks in there, he's like, hey guys, check, I'm a bromo functional group. Wow, I'm really a nerd. Like, look how I'm laughing. I can't even get my words out. So the bromo walks in there, he's like, check guys, I'm the functional group. And everyone sitting at the dinner table literally looks at bromo and it's like, okay, this is really sad. Why am I becoming like this? I used to laugh at English teachers who were like this passionate. Guys, help me. So this bromo, so they all laugh at them and they're like, oh, come on, man, you're not a serious functional group. We're rather just going to name it so that the branches are as low as possible. We're not going to, I really find this one funny, don't I? We're not going to name it so that we're closest to the functional group. Even though this is the functional group, we just ignore that. We're like, come on, dude, get serious. But with all the other molecules, they all made it in life. They get taken serious. So when this thing says, hey, I'm a triple bond, bro, And I actually did that the other night, guys. I was at a bar and I got into a fight. Or some dude was like walking up to me and giving me some attitude. So I said, "Listen, buddy, did you know that I got triple bonds in my body? You should see how all the chicks came and spoke to me after that." Yeah, the girls were like, "Oh my goodness, he's adorable." Okay, no, they didn't say adorable. That sounds terrible. That makes me sound like a little brother. They said he's so gorgeous. There we go. That's what they said. So, yeah, guys, if you want to pick up the chicks when you go out, just be like, "Yo, bro." Just go pick up, fight the guy and just be like, "Yo, bro, listen, you only have single bonds. I have a triple bond. And it has a lot of authority, okay? Okay, guys. So, part of me is a little bit concerned with how funny I find these jokes because they're really not actually that funny. I can smell the silence. It's so bad. Okay, so let's move on. So, sorry if you're also feeling a bit awkward. Like, these jokes are really strange, aren't they? So, where were we? Yeah, so the functional group is on carbon number 2. So we're going to say pent. And then on carbon number 2, we're going to say that there was the functional group, YNE, which stands for alkyne, right? With this molecule, we didn't do that. We just ended it with ane because, as we said, failure of a functional group. We don't take it serious. Okay, so I think the guy that I was fighting with at the bar, he's probably a bromo. All his friends were like, "Yo, what's up, bro?" So, yeah, probably bromo. Okay, I've used that trick before. It's okay. Let's move on. So, I didn't really get into a fight, and I didn't even go out. Yeah. So, pent to ane. And then, okay, now we've got to look at the branches. So, the branches are on carbon number 4. So, some of you are going to say that there's 2 carbons and you're going to say ethyl. Not correct. Each branch, this branch here, is 1 carbon, and then this branch is 1 carbon. So we've got 2 methyl branches. So we're going to say 4, and then 4 again, and then we're going to say dimethyl, pent to YNE. So the naming structure is branches. Then this is the longest chain, and then this is the functional group. Okay, and then compound C is going to be your aldehyde. So once again, we respect the functional group. Well, let's first find the longest chain. Now this one's easy. It's just going to be 4. 1, 2, 3, 4. So we're going to say BUT. For 4 means butane, or BUT. We're not going to say butane because it's not an alkane. And now we respect the functional group. Unlike this lame-o, we respect the functional group. So we start naming over here. Even if there were branches and branches and branches, we wouldn't try to make the numbers as low as possible. We respect the functional group and we begin the naming there. So with aldehydes, we're going to say butan over here, and then we're going to end it with al, butanal. So we don't say butan1al, because the reason is with aldehydes, your functional group is always on the side. Aldehyde always on the side. So it is pointless to put a 1 over there. A fancy word that people say is that's redundant. I once had a student when I used to, when I was still doing like a lot of active teaching, and the student came to my classroom and I remember him saying, "Yes, sir, but that would be redundant." And I was like, "Whoa, okay." Meanwhile, before that, I would just be like, "It's not necessary." And he's like, redundant. Anyways, I don't really use redundant anymore. I just say it's not necessary. So it's, yeah, but they'll mark you wrong. It's not like I'm telling you here you can if you want to. They'll actually mark you wrong. So we don't want to do that, okay? Because it's always going to be on carbon number 1. If it's on carbon number 2, then it's not an aldehyde anymore, then it's a ketone. Okay, so we've done the longest chain. We've done the functional group. Now we need to do the branches, but there aren't any branches. And so you might say, oh, Kev, that's a branch. Not really. That's part of the functional group of an aldehyde. Okay, it's not a branch. So that's literally the name, butanol. Then the last part of this question says, compound F reacts with da-da-da-da-da-da-da-da. Okay, I can just literally see esterification in between there because it says reacts with a carboxylic acid and F is an alcohol. Ho-ho! So if this is an alcohol and a carboxylic acid, we need to just know from our studying and our theory that an alcohol plus a carboxylic acid is a ester. Alright, so it says compound F reacts with a carboxylic acid to form compound S in the presence of a strong acid. Write down the type of reaction. So you can call this esterification, or you can even call it a condensation reaction. So any one of the two. Okay, compound S. Where's S? Oh, we're going to form compound S. Okay. Has an empirical formula of C3H6O and a molecular mass of that. Write down the molecular formula of the... Oh, geez, that's crazy. Compound S has an empirical formula and a molecular mass of that. Okay, it's actually not too bad. Write down the molecular formula. Wow. Okay, so we know that... let me give you a quick example, quick recap of empirical. We don't have to go do the whole empirical thing, but just the following. Let's say you had a molecule that was like C4. This is just a made-up one, C4H10. Actually, no, that's not empirical. C3H7, for example. So if you had to go work out the... so let's say this was empirical. This is just an example, okay? Now, if you had to go work out the mass of that, it would be 3 carbons. Now each carbon is 12, so 12 times 3, and then each hydrogen is 1, so 7 times 1. That would be 36 plus 7, which is 43. Okay, so 43 grams per mole would be empirical. Now we know that the molecular is always a multiple of that. So if I told you that the molecular has a mass of 129 grams per mole, then can you see the relationship over here? If you say 129 divide by 43, you get 3. And so that means that the molecular is 3 times heavier than the empirical, and so you would times this thing by 3, and then it would become, so the molecular would be C9H21, because I multiplied everything by 3. So those are the relationships you need to know. So they tell us that the empirical is that, but then they tell us, so let's quickly go work out the mass of that bad boy. So C3H6O, what would that mass be? Well, it's 3 carbons, so 3 times 12, because each carbon is 12. 6 times 1, because each hydrogen is 1. And then 1 times 16, because each oxygen is 16. Now that would give us 36, 42, 58. 58 grams per mole. So that's the empirical. That is your empirical. Now, or EMP if you're cool like me. What up, what up? So if we then don't say EMP in the test, obviously teachers are going to be like, nee, dat is verkeerd. Okay, so then this one over here is, that's the molecular, which is 116. So if I say 116 divided by 58, then I get 2. So it means that the molecular is exactly double this, okay? So the molecular is going to be C6, because I'm doubling all of these, right? H12O2. So that is compound S, which is going to be the product, which is the ester. So this is the ester. Okay, we're not done. It's quite a weird question. For 3 marks. Crazy. Okay, so they want to know what is the carboxylic acid's molecular formula. Some students would be like, oh, wait, bruh, I'm done. But no, we're not done. That's the ester, but they want to know the carboxylic acid. So if you look at this alcohol over here, it's got 1, 2, 3, 4 carbons. So that's got 4 carbons. Okay. And then the ester has 6, because we've just worked that out. So that means the carboxylic acid would have to have, well done, 2. Okay, so it's a 2-carbon carboxylic acid. So let's quickly draw out a 2-carbon carboxylic acid. Remember, carboxylic acids have the coo, cuckoo, like an owl, like that over there. And so that's what a 2-carbon carboxylic acid would look like. So it's got 2 carbons, 1, 2, 3, 4 hydrogens, and 2 oxygens. For 3 marks, I think these people are, there's a word I want to say, but I can't say it on these lessons like this. But it's an Afrikaans word. Starts with J. I'm just going to say it for all time's sake. These people are just me, bro. With this question here, I just want to give a quick little note. For CAPS learners, which most of you watching this are CAPS learners, because the most popular curriculum, or most learners in South Africa do CAPS, then this question's perfect for you. But for the IEB learners, you could of course still do this question because it's going to give you a very good idea of what to do when you get a question like this in your exam. But I know that in previous years, the IEB does not include ketones as well as aldehydes. If that has changed, well then, of course, you can now do this question. But this question is going to be looking at one of these, okay? I won't say exactly which one. I don't want to spoil the fun. So for IEB learners, you can choose to do this question, or you can decide to skip it. I would actually say try doing it just to see how we would approach this, because in your exam you're going to get something exactly like this, but they're just not going to have aldehydes or ketones. They're going to have alcohols, for example. Okay, so it says here, to which homologous series do the above compounds belong? So what does homologous mean? Homologous means, well, some learners say homologous. I mean, that's perfectly fine. Homologous is what kind of molecule is it? Are they alcohols, alkenes, alkynes, esters, carboxylic acids, aldehydes, ketones? You know, those are the different homologous groups. Now, if you look here, all of these end with the word 1. And guess what? Ketones also have a 1 in them. So these are ketones. Okay? Now, the melting points of compounds A, B, and C are compared. Okay, so here's the melting points of A, B, and C. It says write down the controlled variable for this comparison. So when we do experiments, there are certain things that have to remain constant across the experiments. You can't change too many variables because then you don't know which variable is actually causing the change. So what they are doing is they are only using ketones. So write down the controlled variable. That could be the type of homologous series. So let's say type of homologous. That's the thing that they are keeping constant or controlled. You can also say, you could say that, or you could say functional group, okay? Members of the same homologous series, they will all have the same functional group, okay? Because a functional group is what makes it a specific homologous series. If you have, for example, a molecule that has an OH like that, and all the rest is hydrogen, well, because of that functional group, we would say that this is a alcohol homologous series. Okay? So these two are very much correlated with each other. Okay? Guys, is it weird that while I'm recording, I sometimes like to make sure that there's no background noise. So on my phone, I have a little decibel meter. And let's say, for example, at the moment, there was a washing machine that was in the background. So as soon as the washing machine, sometimes when the washing machine finishes, it plays like a little tune, like do 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 do. But then this one goes on for a long time. And so when that's playing, I actually take out my phone's decibel meter and I hold it up in the air behind my head to try to see if the washing machine is coming through on the video. Quite a nerd, eh? But yeah, the things I do for you guys, look at me, making my life going crazy. So the melting points, okay, where are we? We're here, hey? Not on the controlled variable. So it says the melting points of compounds C and D. Oh, by the way, if you're interested, the decibel, the washing machine was registering a 39 decibel for those of you that are like into this kind of stuff. Look, I'm not into that kind of stuff, but you know, I find it interesting just to make sure the sounds are good. The melting points of compounds C and D are now compared. Okay, so now we're comparing C and D. Okay. Fully explain the difference in the melting points of these two compounds. So what I would always like to do is I would always go and draw it out. Okay. So pentan, that means 5 carbons. 1, 2, 3, 4, 5. On carbon 2, there is the ketone part. Now, the ketone part is just a double bond oxygen. That's it. Now I just go put hydrogens everywhere else. There we go. And then this one is a BUT, so that's a 4 carbon. So let's actually be cool here. So let's do that. And then just remind ourselves that that's that one. And then this one is going to be this other molecule. Okay, so that's got a 4 carbon because it's got a BUT. Then on carbon number, very sneaky. Some of you are going to be like, Kev, they didn't tell us where to put the double bond. Now, be very careful here. You can only... let's first go just work out this 3-methyl. So they're saying that on carbon 3, so I'm just going to go from the left. You could also go from the right if you wanted to. On carbon 3, there's a methyl. Okay, so that's a 1-carbon branch. Okay, good. Now, some of you are like, yeah, but Kev, where do we put this double bond, my bro? Like this double bond oxygen for the ketone. Some of you are like, should we put it there? Now, that is wrong. What you just did there, my friend, is you've just made an aldehyde. Why? Here we go. Aldehyde is when you have a double bond oxygen on the side of the molecule. Aldehyde, side, aldehyde, side. Okay, I'm sure you can't wait to be done with that riddle. Okay, so we're not going to put it there. So then some of you are like, okay, my dude, I'll just put it over here. No, but then you're doing the same thing. Then it's a aldehyde. Why? Because double bond oxygen is always on the side. So the only option you have is there. Because ketones are when you have a double bond oxygen somewhere between 2 other carbons. That's what makes it a ketone versus an aldehyde. Okay, and then so that's it. Now we're just going to go put hydrogens everywhere else. Boom, boom, boom. Okay, you don't need to say boom every time. There we go. Okay, so what else? Okay, so there we've drawn the molecule. Oh yes, I wanted to put the little green thing so we can just remember which is which. There we go. So, we've spoken about melting points, boiling points, when we are looking at branches, right? We've looked at how do branches affect boiling and melting points. Now, let's just go through the thinking behind this again once more. I'm going to use an example here. So, let's say we have a 3-carbon molecule. And then that is obviously going to have a whole bunch of hydrogens, which I'm going to leave out for now. Now, if you put that next to another 3-carbon molecule, then in between those 2 molecules, we know by now that there are these things called intermolecular forces. And those intermolecular forces hold the molecules together. Okay, it's like an attraction force. It's like a magnetic... Okay, it's not magnetic, but you can think of it like that. It's easy to visualize when you think of it like that. It holds them together. And the closer that these 2 molecules can get to each other, the stronger those intermolecular forces can become. Just like with magnets. If you hold the magnets far apart, there's not much happening. You hold them closer together, and suddenly there is a fairly large force. This would be a scenario where there are no branches. Okay, so this is no branches. Okay, let's write that a bit better. No branches. If we do have branches now, then the situation is a little bit different. Then you're going to have molecules that look like that. Once again, in between them, there will be intermolecular forces. However, because we now have this branch over here and this branch over here, we can see that this molecule cannot get as close to this molecule like we had over here. Like if I wanted to, I could have pushed these two molecules much closer together. But by having these branches, they get in the way. The branches get in the way, and the molecules cannot pack together nicely or as well as when there are no branches. So because they cannot pack as closely, they cannot get as close together, it's like having magnets that are further apart, and so the intermolecular forces are not as strong in a situation like this. So if you are a boiler man, so you're a person that likes to boil molecules, okay, I'm just making that up. There's no such thing as a boiler. I mean, you get people called boilers, I think, but that was like an olden day type of thing. But imagine there was a job called a boiler man, and the boiler man's job is to, okay, if it is the 21st century, you can't be saying boiler man. Okay, let's say you get a boiler person, okay, a boiler he, she, they, and okay, if you're playing with fire. So you got a boiler he, she, they, and a boiler he, she, they, their job is to try boil these molecules. Now, how do you boil molecules? Well, you add enough heat so that these intermolecular forces can be overcome, so that these two molecules can then move apart and go into the gas phase. That is what boiling is. You're adding enough energy to try overcome these little forces in between here and allowing the molecules to move further apart, allowing them to convert into gas, because gas molecules are further apart compared with liquid molecules that are closer together. So if you are a boiler he, she, they, then is it going to be easier for you to overcome these forces, or is it going to be easier to overcome these forces? Well, here comes the famous line. Well done if you said that it will be easier to overcome these forces. Why? Because these molecules are not able to pack as closely together, the intermolecular forces cannot be as strong, so it will be easier for the boiler he, she, they to separate to separate the molecules, and so less energy is needed, and so the boiling point would be lower. You don't need as much energy, so the boiling point, the temperature at which it boils, doesn't need to be as high. Okay, so let me now show you how to answer this question in the perfect structured way to get your 4 marks. Okay, so that should lay a good foundation for you to now remember how branches affect intermolecular forces. So now, if we had to look at this one, and of course with intermolecular forces, you must imagine that there was another one like this. Okay, so if we had another one, for example, with 5 carbons, then it would have that, and you'd put them next to each other, because remember, when we are looking at intermolecular forces, we are looking at the forces between the molecules. We're not looking at the forces inside the molecule. Okay, so you got to imagine that there was 2 of them like that. In real life, there's not 2 of them. There's trillions. It's not a number, Kev. I know, but it's a big number. Okay, and so and then here you've got one that has 4. But then it's got this big branch. And so it's this big branch that is what's going to be the deciding factor for us. So we learned now, or we revised over here earlier, that branches, they get in the way and they make it more difficult for the molecule to get close enough together, so the intermolecular forces are not as strong because they further apart and things like that. So we know then that the intermolecular forces for this scenario is going to be much stronger than the intermolecular forces over here. So it would be easier to separate these molecules from each other, because it's easier to pull them apart because the intermolecular forces are not as strong. So the boiling point or the melting point would be a lot lower over here, meaning that you don't need a high temperature to cause it to melt. Okay? And I know earlier when I was talking over here, I might have used the word boiling point, but boiling, melting, I'm not saying it's the same thing. It's definitely not, but it's the same concept. The one is just going from solid to liquid. The other is just going from gas to, or liquid to gas. But it's the same idea, right? We're just changing phase. Okay, so we know then that. Okay, now we need to know how to write the answer for 4 marks. So what you'll do is you'll first talk about the structure. Okay, so we'll say that pentan 2,1 is less branched. Of course, you could say not less branches, less branched than 3-methylbutane. You could also say the other one is more branched. You could say this one is more branched. It doesn't really matter, guys. 3-methylbutane 1. Okay, there we've spoken about the structure. Now we're going to talk about the intermolecular forces, or the strength of them at least. So we could say that the intermolecular forces in this one will be stronger. So the intermolecular forces in pentan 2,1 are stronger than in 3-methylbutane 1. Then we talk about the energy. More energy, or you could say less energy, depending on which one you're talking about, right? Of course, I'm just using one argument, but you could use the reverse. You could say the other way around. Doesn't matter. Let's just clear up some space here. More energy will be needed. Now, for the CAPS learners, most of you watching this are CAPS learners, you can say the word overcome, but you can also say the word break, whereas IEB learners, they don't like you to use the word break. Okay, so more energy will be needed to overcome or break the intermolecular forces in pentan 2,1. Therefore, pentan 2,1 has a higher melting point. Some of you are like, yeah, but Kev, this is not higher than this, my bro. Yeah, but remember, it's negative. So negative 92 is a smaller number than this one. So this one has a higher melting point than this one. So just the layout once again, we spoke about the structure, then we spoke about the intermolecular forces, then we spoke about the energy, and then the conclusion. The table below shows the results obtained from an experiment to determine the vapor pressure. They're probably going to ask us to define it. Oh, so they always do that. Okay, so to determine the vapor pressure of different straight chain primary alcohols. Okay, so we've got primary. Oh, there's a little bit of things we can unpack here together. We can talk about vapor pressure. We can talk about primary alcohols. Okay, so but let's just first see as we go, because I'm going to go on a whole bunch of tangents, and we're not supposed to be doing tangents because this isn't paper 2 maths. Okay, so let's just quickly see something here. Okay, so they've given us a whole bunch of alcohols. Okay, I'll show you. It's pretty basic. So here we've got a 1-carbon alcohol, 3 hydrogens with an OH on it. That's what that is. Then here we've got a 2-carbon alcohol. So boom, boom, and then an OH, and then a whole bunch of hydrogens. Here we've got 3 carbons, 1, 2, 3 with OH. And then you get the idea. 4 carbons, 5 carbons, 6 carbons. Fantastic. Then they've given us the different vapor pressures. We'll definitely have to talk about all of that as we go along. The first question says, define the term vapor pressure. So before we define it, let me explain it. So what we have is, okay, so let's say we are, let's make it easy. Let's say we're busy cooking food. Okay, well, we're busy boiling water, at least for now. So here we've got a stovetop, and we need a pot. So here's our pot. Now our pot has a lid. Okay, so that's our lid. And in our pot, we begin with water. Okay, liquid water. So let's do it like that. Right. We then apply heat. There's our heat. And slowly but surely, even before the water begins to boil, we will already start to see, well, you wouldn't see it because the lid's closed, but we should know that little molecules of water are going to convert from the liquid phase into the gas phase, even before boiling. So, Kev, you're telling me that water can turn from a liquid to a gas before it even boils, bro? That's mad. Yeah, well, it's actually very obvious. I mean, if you go look at your swimming pool, if you had to leave your swimming pool without any pool cover and you leave it throughout summer, the water level will drop. It's not boiling. If you had to climb in there, you're not going to burn. But what happens is that we've got evaporation. And so evaporation is just when the liquid molecules on the surface of the water gain enough energy to escape and turn into a gas. Boiling is when you are doing it on a much higher level and all of the molecules are at the right, all of the molecules are boiling and converting into gas, whereas evaporation is just a surface level tendency. Okay, but that's besides the scope of what we're talking about here. So we've got these water molecules, and as soon as you start supplying a bit of energy, they start converting into the gas phase. So slowly but surely we begin to form some type of vapor. Okay, that's where we're starting to get to vapor, pressure. And so we've got some of these molecules that are turning into gas. So this is in the liquid phase, and then this is the gas phase. Now, these gas molecules, they're going to be bouncing around on the sides of the container. Okay, they're going to be moving around as gas molecules do, and that's going to exert a force on the container walls, and that is pressure. Pressure is just the force exerted over an area. So, and that's why it's called vapor, because it's in the gaseous, vapor phase, and it's a type of pressure. So, the definition is the following. It is the pressure exerted by a vapor in equilibrium with its liquid. So we've got a vapor and we've got a liquid, and we wait until they reach equilibrium, and then we measure the pressure. So a vapor in equilibrium with its liquid. Here's an important part. In a closed system. That's why I put the lid on, right? You wouldn't be able to get a vapor pressure if the lid was off, because if the lid was off, the gas molecules would just be like, see ya, I'm out of here. But because we've confined them, we can actually begin to detect or measure a vapor pressure. Okay, so it's the pressure exerted by a vapor in equilibrium with its liquid in a closed system. Write down a suitable conclusion for this investigation. Okay, well, geez, that's pretty, they're asking us for the end of the story before we've even read the book. So let's first talk about what's actually going on here. So we said that this is a 1 carbon, this is a 2 carbon, 3 carbon, okay? So if we look at a 1 carbon alcohol, and we put another 1 carbon alcohol, because remember, this is all about intermolecular forces, vapor pressure, it's all got to do with intermolecular forces. So that's a 1 carbon, this would be CH3OH. Now, if we had to look at this one, for example, it has 2 carbons in the main chain. So there, and then the rest is all hydrogen. And then let's draw another one over here. There. Now, we know that in this area over here, there are London force intermolecular forces, okay? And over here, London forces. Then with the OH parts, that's where we're going to start getting hydrogen bonding. However, that's going to be a constant throughout the experiment, the hydrogen bonding. Why? Well, if you look at all of them, they all have 1 OH. So the only thing that's actually changing is the length of the carbon-hydrogen part. And that part over there is only London forces. So as we increase the length then what happens is that you have a larger chain length. So you've got a larger surface area for the London forces to act. And the longer you make it, because there's going to be more London forces, the intermolecular forces actually end up becoming stronger. This is not the answer, but I just want to make some notes for you. So as the chain length increases, the molecule surface area increases, which allows more intermolecular forces. Or let's rather say the surface area increases, causing intermolecular forces to be stronger. Okay, so here the intermolecular forces are going to be a lot stronger than this one, for example, because of that longer, there's more surface area, so we've got more space over where the intermolecular forces can act. For example, if you've got 4 carbons, can you see how much more space we have for intermolecular forces compared with over here? So because you've got more space or surface area exposed, the intermolecular forces are overall going to be much stronger. So then, if you then had, this is going to be really cool, if you then had a container filled with, let's say for example, C3H7OH, so C3, and then obviously I always like to show 2 of them because that's what intermolecular forces are all about, with an OH. Okay, then here's another one. Okay, so we've got our container, and we've got our lid. There's our lid. Then if we had another little container filled with this one, CH3OH, and then of course we're going to have a lid. Okay, now what you've got to think of is, think about the intermolecular forces inside here, in between these 2 molecules, and then think about the intermolecular forces here, and think about which ones are stronger. So, I just erased, now all the water's going to spill all over the floor. Sorry guys, man. Okay, so let's see what happens. So what would happen is that the intermolecular forces here would be much stronger, right? So these molecules are holding on to each other much more, whereas these ones, they're not really holding on to each other that much. So which ones will be easier when we start applying heat? Which ones are going to separate more easily? Well done if you said that these ones are going to separate more easily. And so you're going to get more of these ones going into the gas phase earlier on compared with these ones over here. So at equilibrium, which one is going to have more gas? Well done if you said that this one's going to have a lot more gas, because the molecules, because they're easier to separate, they're going to easily be able to go into the gas phase, whereas here you're going to have a little bit less. Okay? So that means the vapor pressure over here is going to be higher than the vapor pressure over here. And that's why we can see that as we go down the table, the vapor pressure is becoming less. Because these intermolecular forces are so strong, it's very difficult to take them and turn them into the gas. And so the vapor pressure is very low. Does that make sense? So there's an inverse relationship. As you increase the intermolecular forces, you decrease the vapor pressure. Can you see that? That should make perfect sense. That should be a nice, easy one to understand. You may have to just watch and think about this a few times, but once you get it, you'll understand it's a very simple concept. These molecules are so in love that you cannot separate them. You're not going to be able to separate them very easily. So there's not going to be that many of them going into the gas phase. Whereas these ones, they're having a little bit of a fight, And it's really easy to separate these ones because the forces in between them or holding them is not that strong. So turning them into the gas phase is very easy. Okay, so it says write down a conclusion for this investigation. So the conclusion will be vapor pressure decreases with an increase in chain length. So as you increase the chain length, you decrease the vapor pressure. This one, write down the IUPAC name of the alcohol with the highest boiling point. Now, this should all make perfect sense to you. Which of these molecules is going to be the most difficult to boil? What do you do when you boil something? You turn it from a liquid to a gas. So you have to be able to overcome all of those forces. So which ones are going to be very difficult? Well done if you said it's this one. These ones are going to be very difficult to separate, whereas these ones are going to be very easy. So these ones are going to require a very large amount of energy to be able to pull them apart. Remember, they are very difficult to pull apart because the forces holding them together are strong. So you're going to need a very high temperature. So that means that these ones are going to have a high boiling point, meaning that you need a high temperature to separate them. And these ones are going to have a low boiling point. So can you see that boiling point is inversely proportional to vapor pressure? When boiling point is low, then the things are easy to turn into a gas, so that means the vapor pressure will be high. When boiling point is very high, it means that it's difficult to separate them, so that means that there will be less of them in the gas phase, so vapor pressure will be low. That should make perfect sense. Make sure you understand that. So it says write down the IUPAC name of the alcohol with the highest boiling point. It's this one over here. So because this is going to be the answer here, we got to know how to name it. Now, there are multiple ways you could have drawn this, but you got to remember that they said primary alcohols, and they also said straight chain. So let's quickly talk about primary, secondary, and tertiary alcohols. So primary, and then I'll do secondary a little bit further down actually, and then tertiary. So with primary, it's the most basic type you can get. It's going to be like that. Why is it a primary? Well, if you look at this, if you look at the OH, then you look at the carbon touching that one. Then I want you to look at how many carbons are connected to this one. Well, that would some of you are going to say 2, but I'm talking about directly connected. So that would only be this one over here. And so there's only 1 carbon. That's why we call it primary. If we look at secondary, well, then you're going to get a structure that looks like this. Not like that, like that. So look at the OH, then look at the carbon that's touching that OH. Now, how many carbons are directly touching this one? Well, there's 1, and there's 2. Now, with tertiary, well, that's going to look like this. So you're going to have an OH. Okay, I'm going to... come on. It's going to be something like there. Okay, you get that's an OH. And then we're going to put a carbon up here. Okay, so you look at the OH. Then you look at the carbon touching that. Now, how many carbons are directly touching that one? Well, there's 1, 2, 3. And so that's what we call tertiary. So we have primary. So it's going to be a basic one like this, where the alcohol is going to be on carbon number 1. So it's a 6 carbon. So that's going to be hexane, and then alcohols always end with OL, but we must say that it's on carbon number 1, the OH, and then there's no branches, and so that would be the name over there, hexane 1-ol. Okay, this last question says the experiment is now repeated at 320 Kelvin. So it was originally at 300, so they're doing it at a slightly higher temperature now. What would happen to the vapor pressure? Well, it's very easy. Think about this. if you add more heat, are you going to cause more molecules to go into the gas phase? How do you get things to go into the gas phase, by the way? You have to be able to separate the liquid molecules from each other. And the way you do that is by adding energy. So, if you are now using a higher temperature, that means you're adding more energy. So you're going to have more molecules that are going to be able to now go into the gas phase. So that means that the vapor pressures for all of these will increase. So you're just going to say increase. Because when you add more temperature, you are adding more energy, and that energy will allow more molecules to be separated from each other in the liquid phase to then go into the gas phase. And that raises your vapor pressure. So just keep a note here that there will be more questions on the next slide. There we've got there, and there we've got there. Okay, so it says the flow diagram below shows how compound A can be used as a starting reactant to prepare two different compounds. 1, 2, and 3 represent organic reactions. Right, so the first question says, is compound A primary, secondary, or tertiary haloalkane? So please always draw it out, okay? So I just start on the left-hand side, and I don't look at any of that, I just start piece by piece. So the first part is a CH3. Okay, CH3. There we go. Now that part's done. Then there's a carbon. Okay, carbon. Then there's a CH3. Now some students are going to be confused. They're going to say, does that mean it's part of the chain, or does it mean it's a branch? Well, it cannot be a chain, because you can't put a CH3. That would only be a CH2. Because if you put the other hydrogen, well, then you've ended your whole chain. So rather put it as a branch. So you can either go up or down. So I'm going to go down like that. So now the CH3 is done. Then there's a Br, okay? That can't be there. You never get a Br somewhere in the middle. Like, how weird is that? So it has to go there. Then there's a CH2. Okay, that makes sense. A carbon with two hydrogens. And then a CH3. There we go. And then obviously all of these are hydrogens, right? There we go. So just like with primary alcohols, secondary alcohols, and tertiary, we can do the same with haloalkane. So what you do is you go find the halogen. So there's your halogen, okay? Then I want you to look at the carbon that is directly touching that one. So there it is there. Now I want you to see how many carbons are directly connected to this one. Well, there's one over here. You can't count this one. That's not directly touching this one, okay? Then there's one over here, and then there's one over here. So that's 3. So that would be tertiary. And it says give a reason for your answer. So you could say the halogen is bonded to a carbon which is itself bonded to 3 other carbons. Moving on to this one, it says consider reaction number 1, and it says besides heat, write down the other reaction condition. Okay, so we need to know, I should have actually kept compound A. So let's quickly just draw out compound A once more. We had a CH3 like that, and then we had a CH3 down here. We had a Br, and then we had CH2 and CH3. Okay, and I'll go put all the hydrogens. And now they're telling us that that is going to be converted into alkene. Alkene. How do I know that that's an alkene? Because I know that alkenes have a general formula that is CnH2n. So that means that the hydrogen always has double the carbon, and 5 and 10. So it's definitely going to be an alkene. So what we'll probably have is we're going to have our normal 4 carbons, which we still have here in this main chain, and we would never lose that branch over there, so that's still going to stay. And so there's the 5 carbons. Now, we got to try to figure out where the double bond is. I don't even know if we're going to need to know that for this. They are going to ask us for the structural formulas later on. Okay, so let's just do it anyways. Excellent. So we got to try to figure out where the double bond is going to go, because alkenes have a double bond. So check this out. There's no Br over here. So we're definitely going to lose this Br. So let's go fill in all the, oh no, we don't know if we're going to lose a hydrogen. Okay, so we know that that's going to be lost, this Br. Okay, that's gone. Then, to be able to make a double bond, we need to lose something on either this carbon over here or this carbon over here, so that we could then put a double bond either there or there. But you can't just choose whichever you feel like. You got to use the organic chemistry rules, which is that whole riddle that we sometimes say with the richer get richer and the poorer get poorer. So richer get richer, and then the poorer get poorer. And remember, when we're doing that, we're talking about hydrogen. Okay, now this is going to be an elimination reaction because you're taking things away. You're taking things away from this molecule. So we're not going to look at the richer get richer part. That's only when you are busy with addition. So let's make a little note here. That's only when we are doing addition. What we're doing is the poorer get poorer. And that is where you do elimination. Okay, so the way it works is you don't look at this carbon here because that carbon already lost the bromine. So you look at the carbons next to that one. So it's going to be this one, or technically you could even look at that carbon as well because it is touching it. So you then look at those carbons, those three carbons, and you look and see which one is the poorest in hydrogen. So we know that this carbon here has 3. It's got 1, 2, 3 hydrogens. Okay. Then this carbon over here also has 3 hydrogens. You see them there? And then this carbon over here only has 2. So that means that this carbon is the poorest, and the riddle tells us that the poorest one gets even poorer. That means that we are going to lose one of these hydrogens. If you wanted to lose the one at the bottom, that's okay. They don't really, in the exams, they don't mind about that. It doesn't matter at all. So let's eliminate this hydrogen. So that means we've lost this thing over here. And then everything else will stay the same. So let's go draw in everything else, and then you'll see how the double bond fits in. Okay, now you see we have a bit of a problem because we've lost the Br and we've lost the hydrogen. But now, if you look at this carbon over here, it only has 1, 2, 3 bonds around it. If you look at this carbon over here, it has 1, 2, 3 bonds around it. And that is where we can now use the double bond to make sure that we have 4 bonds around this carbon and 4 bonds around that carbon. So that is the elimination reaction over there. Now, I know that that's not, we didn't need to do that for this question, but I wanted us to have a very good visualization of what exactly is going on here. So it says, besides heat, write down the other reaction condition needed. So if you've ever looked at my diagrams where I show you all the different organic reactions, we always have at the top here, we've got alkanes, and then we've got an arrow going to haloalkane, for example, and then we've got arrows going back to alkene, right? And obviously there's a whole lot more reactions. There's plenty of reactions, but there's this one, and then we also know that there's one that goes down to alcohols. And we can also go from alcohol to haloalkane. We can go from this way. We can go this way. We can go... I've showed you this diagram before where we've got all these different reactions. But what's important is the one we're busy with now, which is when you have a haloalkane, okay, which is here, and then you end up with an alkene. So it's this reaction over here. And so I've spoken to you guys about this at length before, where with haloalkanes, you need to be careful. Because haloalkanes, they've got 2 different reactions they can do. You can go from a haloalkane to an alkene, but you can also go from a haloalkane to an alcohol. And this is the one where both of these reactions, they make use of, so let's write out the conditions here. Both of those reactions make use of a strong base. such as sodium hydroxide or typically potassium hydroxide, one of those. But if you use a concentrated strong base, then it does one type of reaction. And if you use a dilute, then it does the other type of reaction. And you need to know this. So I've spoken to you guys about this before. If you go from a haloalkane to an alkene, we said that is elimination. And we've said before that elimination is very aggressive, right? It's a very aggressive kind of thing. Like if someone says, hey bro, you are eliminated. Like that sounds pretty violent if you ask me. Whereas if someone says, hey bro, you need to come off the field so that I can come back on, so that I can come onto the field, so I need to substitute. We need to make a substitution. That's not so bad, okay? But when someone says, hey bro, you out, you eliminated, that's aggressive. So what word is more aggressive? The word dilute or concentrated? So it's definitely concentrated. Concentrated is a more aggressive kind of thing. Dilute is like, hey bro, I made you some Oros, but I decided not to add that much Oros, so it's a bit dilute. Like that's a bit lame, it's boring. But if someone's like, hey bro, I decided to give you half a glass of Oros and half a glass of water, it's concentrated, it's aggression. I don't know, like I think you can make any word sound aggressive by the way you say it. So yeah, I don't know. But the word concentrated must make you remember elimination. Elimination, aggressive, yeah. So I don't know how you want to remember that, but you just got to remember that. When they use concentrated, that means elimination. Okay, so concentrated, elimination. Dilute, substitution. Got it? So it says here, besides heat, write down the other condition needed. You would need to use a concentrated strong. Those are not the same things, right? This is not the same as this. They're two different things. So we're using a strong base. A strong base is just a base that loves to dissociate, such as potassium hydroxide or sodium hydroxide. But being concentrated is another, it's not the same as being strong. Okay, you can get something that's strong and dilute as well. And then because they didn't tell us what base we're using, I did check on the memo and they will not mark you incorrect if you put something like concentrated NaOH or concentrated KOH. You can also do that. Okay, but you must use the word concentrated. That's a non-negotiable. Right, so it says besides, okay, so we've done that. 4.2.2. Write down the type of reaction that takes place. Well, that is elimination. You could also call it like you could call it dehydro, because we're getting rid of a hydrogen and we're getting rid of a halogen. So you could call it dehydrohalogenation. Let me write that better for you guys quickly. Dehydrohalogenation. And then the last question for 5 marks, using structural formula. So these are structural formula. Write down a balanced equation. Okay, so this is not going to be good enough. We actually need to go add a few more things. So these drawings that we do have, we are going to keep those, but we need to add a few more things here. So now that we're going to go write down the reaction, I'm not sure if you've watched that video where it was one of my reaction videos where we spoke about a haloalkane going to an alkene, but there are two methods that different textbooks and different teachers in South Africa use. We've got method 1 and we've got method 2. You remember that video that I've done before with you guys where we've looked at that. Okay, so I will do both. On the memo they only do the one, but both of them are valid, and I'll show you how to do it for both techniques, okay? So for the first one, I will treat the base as a reactant, and then for the second one, I will treat the base as almost like a catalyst. Okay, so let's do method number 1. So this will be number 1. So we're going to treat the base as a reactant. So that means you're actually going to say plus. Now, let's use NaOH. You could have chosen KOH, but I'm just going to go with NaOH. Okay, put an arrow.
now here's your reactant. You've got this, and then you're going to have NaBr. I will explain now where that comes from, and then H2O as your other product. So the Na combines with the Br that came off, and they become sodium bromide. And then the H that we gave away, remember that H and that OH, they combine to become water. Okay, so that is how option number 1 would look. Now I'm going to do option number 2. Okay, so I'm gonna erase all of this now, and I'm going to do this, and I'm going to do this. Now with option number 2, we don't say plus because it's not a reaction with the base. The base is like a catalyst. So what your teacher might do is they just write it at the top here. So maybe NaOH. Okay, now what happens, oh, and then we've got that. Now what happens is that your product is going to be this over here plus HBr. Let me explain. So the NaOH is now not getting involved in the reaction. So we don't see any Na and OH over here, and we don't see any Na and OH in the reaction over here. So all that happens now is that the H and the Br that were eliminated, they just combine to become that over there. Okay, if you're unsure about what I've just done, then go look at that video in the playlists on the reactions. It's where we have a haloalkane turning into an alkene, and in that video I do share 2 different methods that are used in by teachers in South Africa. This question says, consider reaction number 2. Okay, so this is reaction number 2, where we're taking compound B. So let's immediately go draw compound B before we even look further. We looked at compound B in the previous question, so we should still remember all about that. Or something to do. Let me just go back here. It was this one, remember? Okay. There. There. Boom. Okay, so that's what we had, and then they said that we are going to convert that into this. Now, if you look carefully here, there's 5 carbons and 5 carbons. But then there's 10 hydrogens, and now there's 12 hydrogens. That means that they've added 2 hydrogens, and then here there's no oxygen, but here there's 1 oxygen. So they've added water. So what will happen if you take a alkene and you add water to it? Well, if you think of water as H connected to an OH, we know that the hydrogen will end up going here or here, and then the OH will go to the other one. So if the hydrogen ends up going here, then the OH would go there, or vice versa. We'll have to figure that out. So we're going to develop an alcohol as a product. For those of you that have studied my reaction diagrams before, then you should remember we've got alkanes over there, we've got haloalkanes over there, alkenes, and then alcohols. And then we've got, so what we have here is we've got an alkene that is being converted into a alcohol. Okay, and so to try figure out what the major product is going to be, we need to go back to richer get richer, and the poorer get poorer. And remember, we're talking about hydrogen. So, because we need to try figure out where's this hydrogen going to go, and where's this OH going to go. So when we are doing an addition reaction, where you're adding something onto another molecule, then we only look at this part of the riddle. Okay, we don't look at the poorer get poorer. That's only with elimination, like we looked at in the previous part of this question. So what we do is what happens is that this double bond is going to be broken up into a single bond, and then you're going to have attachment points now over there and over there. Let me explain that. Because here when you have a double bond, you can see that in this carbon there's 1, 2, 3, 4 attachments or bonds, and then here you've got 1, 2, 3, 4 around that carbon. But now what happens is that if you break that double bond, then what that allows is extra 2 points over there. But what you'll notice is that each carbon is still surrounded by 4. See that? And so that's what happens over there. Now we got to try to figure out this hydrogen. So it says that the richer get even richer. So if you look at this carbon, and if you look at this carbon, how many hydrogens did they have at that moment? Well, this one over here has 1 hydrogen. There it is. This one has absolutely 0 hydrogens. Can you see that? There's no hydrogens. So who's the richest in hydrogen? Well, this one's the richest. And what does the riddle say? The richest one gets even richer. And so this hydrogen's going to end up going there, and then the OH would end up going over there. So let's quickly draw that in. So your product would then have the hydrogen over there and then the OH over there. If you did it the other way, that is wrong. That is called the minor product, but they would like us to do the major product. Okay. So it says write down the structural formula. That is the structural formula. And you must remember that if your diagram is a bit not backwards, but different to mine, like if you have the OH on this one and you've got this part over here, that's fine. That's absolutely fine. Okay. This question says, name or formula of the inorganic. Inorganic is a molecule, something that doesn't have carbon. Okay. So that's going to be the water. The water is what we need. Remember, I just told you we're going to add water. Okay. So you could either say H2O or you could say water. Then it says, what is the type of addition? Well, with the types of addition, we've got halogenation, hydrohalogenation, that's just completely wrong. So we've got hydrohalogenation, halogenation, hydration, hydrogenation. So here we are adding water. So that one is called hydration. Just like if you drink water, you are hydrating. Here's the last part of this question. So it says, consider reaction number 3. It says, write down the type of reaction. So let's see what we have here. We've got a haloalkane. I don't care what this is. I just want to know what kind of molecule. Like, I don't need to know exactly what it is. I just want to know the homologous group. And then here we've got an alcohol. Okay. So on our reaction diagram, this would be alkanes. Come on. Alkanes. Alkenes, and then haloalkanes, alcohols. And so what we have is we have the haloalkane turning into an alcohol. Whereas in the previous part of this question, when we were looking at, I think it was this one over here, this is the one where we had a haloalkane going to an alkene, where we had to use a concentrated strong base. Now we are going from a haloalkane again, but now we're going to an alcohol. And if you were listening carefully, I reminded you at that time where we said that a haloalkane can have 2 possibilities. It can go to an alkene or it can go to an alcohol. In both of those, you have to use a strong base. Strong base and a strong base. But in this one, where you're doing elimination, we use concentrated strong base. But in this one, we use a dilute strong base. And if you are going from a haloalkane to an alcohol, that is just a substitution reaction. If you think about what we... Oh no, that was a previous thing. If you think about the way it works, if you have a haloalkane, okay, let me just draw a random haloalkane. So something like, let's say, I'm just making up a random one, okay? It's not the one we have in our example, yeah? And you react that, for example, with NaOH, but not a concentrated. You have to use a dilute. Otherwise, if you use concentrated, it will do elimination like we saw in the first part of this question. Then all that happens is that this OH is literally just going to switch places with the Br. So they're just going to switch places. Okay? You're not going to form a double bond. We're not eliminating. We're just substituting. So you would end up with something like that over there, and then you'd be left with NaBr. That's just an example, but can you see that we literally just switch these 2 things out? So it says write down the type of reaction that takes place. Substitution. You can also call it hydrolysis. We can also call it hydrolysis. Okay, that's not a very common way of calling it, but it is correct. Now it says besides heat, write down the other reaction condition needed. Well, this is where you would say use a dilute strong base. You must use the word dilute. You could say dilute NaOH. You could say dilute KOH, but you could also just say dilute strong base. Here we have a typical question 5 kind of exam question. Now these question 5s, they're so long. They always have like these big tables, and then you've got this drawing over here, and then we've got a syringe, and then we've got another graph. It's a lot, these question 5s. So let's see what they tell us here. So that's also what I want to say. Just remember, there are going to be more questions, okay? So 3 experiments, A, B, C, are carried out to investigate some of the factors that affect the rate of decomposition of hydrogen peroxide. The balanced equation for this reaction is the following. Okay, so they give us the balanced equation. Then it says, identical samples of hydrogen peroxide are used in each experiment. The conditions used are summarized in the table below. Okay, so we're using different temperatures for some of them, and then we're using without catalyst or with catalyst. Okay, so this is all about reaction rates, collision theory, things like that. So the first question for 4 marks, nice opening question there for 4 marks, geez, like, in which experiment is the reaction rate going to be higher? Use the collision theory to explain your answer. So look at everything else is the same, temperatures are the same, and it's just a catalyst, okay? So we know that a catalyst will make the reaction faster. So it says, in which experiment is the reaction rate higher? So immediately we will say reaction B. Okay, so let's just write that over here, reaction B. Now, we got to go through the collision theory. Now remember with the collision theory, we said that for a reaction to be able to occur in the collision theory, we said that we need 3 things to consider. Number 1, the molecules must collide. The molecules need to be able to bump into each other if they are going to react. Okay. Number 2, if you guys, let's say for example you want to meet a lovely lady, for example. Now, if you let's say you are you're looking out your window one day and there's this beautiful girl walking past. Okay. Now, if you want to have any chance of meeting this girl or taking her out on a date or anything, you're going to have to get out your room. You're going to have to take off your wife beater, your white vest with your cheese curl puff stains on it, that because you've been gaming so much, bro. And you're going to have to put on some nice pair of clothing, and you're going to have to get out the room, and you're going to actually have to go and walk up to the girl and collide, if you know what I mean. You're going to have to not bump into her, but you're going to have to cross her path for any kind of reaction or chemistry. That's so funny because we are doing chemistry, to be able to take place. By sitting in your room and just watching out the window, bro, it ain't going to happen, okay? You got to put the gaming PC away for a bit. You got to clean up your shirt, man. You can't have cheese puff curls in your beard. Okay? So, I don't know why this is suddenly becoming like a drill sergeant Kevin moment. But so number 1, you got to make a collision. Okay? You can't so for molecules, if 2 molecules see each other and they want to collide, they can't just look at each other from across the room. They have to physically go and collide for there to be any kind of chemistry taking place. Okay? So number 1, they have to collide. The molecules have to collide. Okay? Number 2, oh, it's had a funny vision. All the guys after watching this suddenly running around, running into the girls and like bumping into them. I don't mean physically collide, guys. I just mean cross paths, okay? And then number 2. Number two, what was that? Oh, the molecules need to have enough energy. They need to have enough energy, okay? So, guys, if you're going to walk up to the girl and you're going to be like, hey man, how's it going? Yeah, no, I'm almost dead. I'm running on about 3% energy at the moment. Yeah, it's chilled, man. Like,
what are your chances of a good collision or a good reaction? What are the chances? Not going to be very good. But if you walk up there and you're like, hey, how's it going? Okay, no, that's a bit too much, too much. Come on, Kev, you got to read the room, bro. You can't be that guy. Okay, you don't want to immediately land yourself in the friend zone either. Okay, you got to play it cool a little bit. You got to be like, hey man, what's up? Okay, no, you can't do that either. Okay, let's just say I'm not actually that good with girls. Okay, I'm a fraud. What's it called? My pickup game sucks. So, yeah, I'm actually just going to stop there. I'm feeling like I've let you guys down right now. Like, I can't even think of a good energy. Like, I can't even pick up the right vibe of energy. Let me give it one more go. So you got to walk up there and you got to be like, hey, how's it going? Lovely weather we're having. No, you can't use the weather thing. Okay, let me try again. Hey man, so listen, I'm new here, and okay, maybe don't say hey man, just be like, hey, how's it going? I'm quite new here. No, I think I'm talking a bit too fast there. I sound nervous, don't I? Okay, let me try one more time. I've got this now. Hey, how's it going? My name is Francie. I come from Paraguay. Okay, no, that would be from France. Okay, last time. So we're gonna say so energy. We're gonna say, hey, how's it going? I'm quite new here on the campus. I'm lost. Would you mind letting me know where this classroom is? And then you give the classroom number. You see, now your energy's good. You're not coming across as too needy. You're not coming across as like overly weird or creepy. And yeah, you're not coming in there like you're immediately trying to flirt or whatever. You got a good balance. You got it going, okay? So you need to have the right amount of energy. Okay. And then number 3, orientation. Okay, now I'm not going to even try to relate that back down to walking and talking to girls, because yeah, that's probably things are gonna get weird. Okay, but you get it, guys. So I think I'm gonna stop with the whole like using this as a way to talk to girls and stuff now, and to the girls that are listening to this right now, feel free to comment and give me some more tips, especially on number 2. You could see I was struggling a little bit over there. So, okay, let's get back to serious now, guys. I know this is serious for you guys, and it's serious for me too. So, okay, so for molecules, now we're not talking about people anymore, but for molecules to be able to react, there needs to be a collision. Okay, so they have to be able to collide. They have to have the right amount of energy, and they have to collide in the correct orientation. They have to be facing in the correct direction, for example. Okay, so let's carry on with this question. So we said that it's reaction B. Now, what does a catalyst do? Well, a catalyst does not allow the molecules to collide more or less often. A catalyst does not change the orientation. What a catalyst does is it is able... Can you remember what a catalyst does, guys? It lowers the activation energy. So let's quickly write that down. A catalyst... This is not part of the answer. I'm going to show you how to write the answer now, but I just want to give us some notes. A catalyst lowers activation energy. And what is activation energy? Well, activation energy is the minimum amount of energy needed for a reaction to occur. And I've spoken about this in detail before. So what a catalyst does is it lowers the activation energy, and the activation energy is the minimum amount of energy needed for a reaction to occur. So if the activation energy is lowered, then it will be easier for the molecules to react because they don't need to have as much energy in order to react. It makes it easier for them, okay? So we're going to say reaction B. Let's write our answer over here. So we're going to say reaction B. We can then say catalyst lowers the activation energy, which will cause more molecules to now have enough energy
for an effective collision. And then we can say more effective collisions per unit time will take place. This question says that the Maxwell-Boltzmann distribution curves for X and Y are shown below. Identify the curve that represents experiment C. Oh, okay, I understand. So they've given us 3 experiments, but these 2 are only going to be 2 of them. So we know that a catalyst does not move this graph. If you've watched my video on Maxwell-Boltzmann curves, you would see that a catalyst does not have the ability to move the graph, okay? It only lowers the activation energy. Now, if we look at temperature, we know that as you increase the temperature, the energy increases, right? So for example, if you have a Maxwell-Boltzmann curve that originally looks like this, and then let's say here we've got energy. Now if you look at this point over here, if all of a sudden the temperature gets increased, then you need to remember that increases the energy of the molecules. It increases their kinetic energy. So this kinetic energy will go there. So now all of a sudden that part will be over here. So what happens is that the entire graph ends up shifting to the right, and for some reason it also lowers a little bit. So you're going to end up getting a graph that does something like that. So this graph here is the one that is shifted to the right, and so that would be C, which is the higher temperature graph. So it says identify the curve. They didn't say Y. Okay, they tell us here that the volume of oxygen gas produced in experiment B during the first 3.6 seconds is collected in a syringe as shown below. Okay, so they've collected about, so this is 160, 324, 86, 40. So in between here is 160, I think, 640 minus 480. Which is 160, okay? And then we'll half 160, because from there to there is 160, and so half of that is 80, and so 480 to plus 80, this would be 560. Okay, so work that out however you feel comfortable, but you should eventually end up with 560, and then just use their units, which is centimeter cubed. Okay, they tell us that the balanced equation for this reaction is this one over here, which we also had up here. Now it says calculate the mass of water that was produced during the first 3.6 seconds, okay, which is also what we have over here. Take the molar gas volume to be 24,000 centimeters cubed. Okay, so what we can do is we can realize that there is 560 centimeter cube of oxygen that was produced. That's a gas, so we can use this formula over here. N equals to V over Vm. But now normally over here we use 22.4 decimeter cube. But that's only when we are at STP. But we are not at STP. They tell us that because STP is 0 degrees Celsius and things like that, but they tell us we're at 25 degrees Celsius. You might be saying, Kevin, isn't 25 degrees STP? No. 25 degrees is sometimes what we talk about as standard conditions with electrochemistry, where you have 25 degrees, 1 atmosphere, 1 mole per decimeter. But that's different. So that's standard conditions, but now we're talking about STP, which is standard temperature and pressure. So it sounds the same, but they're two different things, okay? So STP is 0 degrees Celsius, and that's where you use 22.4 decimeters, which is the same as 22,400 centimeter cube. But now we are at a higher temperature, and so your gas is a little bit more expanded, and so we're using 24,000 or 24 dm cubed, if that's what you want to use. So they're giving you a value to use for Vm.
Okay, so when you use this formula, the units do not have to be in decimeters, but as long as these two have the same units. So we could then say that the volume that was collected is 560. Now that's measured in centimeter cube, so I'm just going to leave it as centimeter cube. And then this one here is also also centimeter cube, so we're going to say 24,000. And if you had to work that out, now that'll give us 0.023 mole. And that is for oxygen, right? Because this was oxygen, and yeah, this value here, molar gas volume. Remember, this is a gas volume formula. So, and you might be wondering, Kevin, why did you start there? Well, there's actually nowhere else you could have started. I mean, if you used any other value, this 24,000 is a molar gas volume, and this is a gas. So you could only use that, and then this was also the gas. And so those are the only ways we could have started. Okay, so what's nice now is that we have the moles of oxygen, and once you have the moles of one of them, you can get the moles of any of the others that you might need by just using the mole ratios. So what we could say is that the moles of H2O to oxygen in the, no, let's actually, I've never done this before, but let's say in the equation, or let's say in the reaction, and then this is what we actually have. Okay, so in the reaction, 2 moles of H2O goes with 1 mole of oxygen, but what we actually have is 0.023 moles of oxygen, but we don't know how much H2O we have. So here is what we can do. We can cross multiply. So we could say 2 multiplied by 0.023 equals to 1. We can make this an x. And so x would end up being 0.046. If you're getting a slightly different answer to me here, maybe you're rounding a little bit differently, the memo understands that, and the memo gives you a range. I will give you the range value, a range of answers that you're allowed to get when we get our final answer here. Okay, so x will be 0.046, so therefore the moles of H2O is 0.046 mole. So it says calculate the mass. Okay, now to get mass from there, we're just going to go to N equals to M over capital M, and so that's going to be 0.046 equals to the mass over the molar mass of water, which is going to be 2 hydrogens and 1 oxygen. And so we now end up with 0.046 equals M over 18. And so if you then take the 18 to the left, you end up with a mass of 0.83 is what I'm getting. But based upon the rounding, they give you a range that you can get, which is 0.72 all the way up to 0.90. So it's quite a wide range, and that's mainly because of this area here with different rounding, okay? So, yeah, rounding's always a bit of a thing, but the memo does give a range that your answer must fit inside. Now, this question says, the graph below, okay, so all of this was the same, but it says the graph below, which I've put over here, not drawn to scale, is obtained for the mass of oxygen gas produced over time. So what we can see is that oxygen gas is being produced. So as the time, or sorry, here we can see oxygen gas is being produced. So as the time increases, we can see the amount of oxygen gas is becoming more, and then eventually it stops over here where the reaction has ended. Okay, now this first question says, write down the rate of production for the interval 30 to 36. Okay, well, there is absolutely nothing happening over there because the mass of oxygen is remaining constant. So how fast is the reaction going over there? It's not going at all. So you're going to say 0. And you could give units, but I see on the memo they didn't even expect it. The units would always be the y-axis over the x-axis, so that would be grams per second. Because remember, rate is how fast, and you can actually measure that using the gradient. And gradient is always y over x. But now, if you had to draw a tangent over here, well, it's flat. And so there we can also see it's 0. Okay, now this question for 1 mark. Will the rate of the reaction in interval 3 seconds to 9 seconds, so in that area there, be greater, smaller, or equal to the rate in the 9 to 20 part? Well, it's definitely going to be smaller, but of course they're going to ask us to explain that. Oh, no, they don't, but I will explain it. So 9 to 20. Just by looking at the gradient, you can see that the gradient of the green part is a lot steeper. See, there's a steep gradient, but then here it flattens out a little bit. Now, so the answer is definitely going to be, wait, which one did that one? Will the rate of the reaction in the 3 to 9? Yeah, that one's going to be greater. Now let me just explain why. It all comes down to the collision theory. So I want you to imagine when a reaction first starts. When a reaction first starts, you've got a lot of reactants moving around, colliding, reacting. But as they start colliding and reacting, they start converting into product. So as they start converting into product, do we then have more reactant or less? Well, then we have less reactant. That means there'll be less reactant bumping into each other, there's less collisions taking place, and so the reaction rate begins to slow down. So you'll see that the reaction rate is always going to be the fastest in the beginning. You can see how steep it is, and then it begins to. So if I draw a tangent there, it's like that. If I draw a tangent there, and if I draw a tangent there, and if I draw a tangent there, and if I draw a tangent there, you can see that the tangent or the gradient is just becoming more and more flat. That is indicative of a reaction rate that is slowing down. Okay, because the reactants are being used up, so there's less of them to react. It's like this, guys. Let's say we've got a room. Let's say we've got an assembly hall. And let's say in this room there are 30 people. Okay, just imagine you and your classmates. There's 30 of you. And you all have like these big beanbag things around you, or like these big, like those, I don't know, like something with like a big jumpsuit on that you can put on, and you run around and you're just bumping into people. In the beginning, are you going to be bumping into people a lot or not that often? Quite a lot, right? Because that's where the most people are. But let's say that every time you bump into someone, you and that person have to go sit outside over here. Okay, so then as that carries on, are there going to be more collisions taking place or less? Less, right? Because in the beginning you had a lot of people running around the room, running around, bumping into each other. But as they bump into each other, they have to go sit outside. You can think of that as converting into products. And so now you maybe only have 8 people running around, and so there's going to be less collisions taking place because there's less reactant molecules. That's how it is. Now, for 5 marks, it says that the average rate of decomposition of hydrogen peroxide is 2.1 times 10 to the minus 3 moles per second. So what they're saying is that this is a reactant, so it becomes less, right? Now they're saying that it's decomposing at a rate of 2.1 times 10 to the negative 3 moles per second. So every second that goes by, the amount of H2O2 is going down by this amount of moles. Every second it's going down by that. Okay? Now it just says calculate the value of T on the graph. Okay, it's very easy. If we know how fast this amount of stuff is decreasing, then we can just use the mole ratio to work out how fast or how many moles per second is this one increasing. Yes, we could also look at this one, but we don't need to because the graph is all about oxygen. Okay, so check this out. If we know that the time is there, we can just go up to the graph, and then we can just go look at the y-axis, and we can see that it's 0.9. So that means the mass of oxygen is 0.9. So we can say 0.9 grams. What we can then do is quickly turn that into moles. So we can just use N equals to M over capital M. And then we can say 0.9 over oxygen. Now, oxygen is diatomic. You can see there's a 2 there. And so we're going to say oxygen is 16, but there's 2 of them. So it's going to be 0.9 over 32. And once again, it's always a bit awkward how to round off. So on the memo, once again, they are giving you a range. So I'm just going to round off to 0.028 mole, and that is oxygen. I'm then going to just work out what is the moles of H2O2. So the moles of, here we can use the whole, how is the reaction balanced? And then what do we actually have? Okay, so if we have H2O2 to oxygen, we can see that it's in a 2:1 ratio. So 2:1. So we can say 2:1. And then the actual, well, the amount of oxygen is 0.028. And some of you might be wondering why we're using 0.028, whereas in the previous question we had oxygen as 0.023. They're 2 different questions completely. Okay, I should have added that, but I didn't think it was going to become a thing. But yeah, they're 2 different questions. In this question, we were only talking about at 3.6 seconds, which was like over here, for example. But now we're talking about a totally brand new time. And then here you can just say x. And now here's where you can cross multiply. So you could say 2 multiplied by 0.028 equals to 1x. And so that'll be 0.056 equals to x. Therefore, the moles of H2O2 is 0.056. Okay, now check this out. They tell us that the hydrogen is decomposing at that speed over there, 2.1 times 10 to the minus 3. Let's actually just write that as a better number. So 2.1 times 10 to the minus 3 is the same as 0.0021 moles, so it's mole, per second. So check this out, guys. The amount of, let's write this a bit better. The mole of H2O2 we said was 0.056 mole. So the total amount of hydrogen peroxide that has reacted is 0.056. The hydrogen peroxide is reacting at 0.0021 moles every second. So then how many seconds would you need to eventually get to 0.0056? Or what you could do is you could just say 0.0056 divided by 0.0021, and that'll give us. So what you could then do is just say this is the total, 0.056, and you could simply divide that by 0.0021, and that'll give us 26.67 seconds. Now that makes sense. It's somewhere between 20 and 30. So 26.67 seconds, okay? Now, you might be a bit confused with this part. I'll make it easier for you. Let's say you pick 80 apples in a day. Okay? But your rate is, let's say, 5 apples per hour. Then how many hours would you work for? Well, you would take your total amount of apples that you can pick divided by your 5 per hour, and that would end up giving you 8 hours. It's the exact same concept. This is the total amount we accumulate that H2O2 reacted. This is what it can do per second. So then it would work out to 26.67. Now, if you did different rounding, the range of answers that you are allowed to get for this one will be 26.67 all the way up to 28.57. So this question carries on onto quite a few slides. So here we've got the first 2 questions. Then we've got 6.3 and 6.4, 6.5, and then 6.6. Carbon reacts with sulfur according to the following balanced equation. The system reaches equilibrium at a temperature T. Don't be asking us to calculate that now. In a sealed 2 decimeter container. The Kc value is 9.4 at T. What's going on? Explain the answer. How will the amounts, if the concentration, show all your workings. What do the parallel lines? Okay, it doesn't look like we're going to have to calculate T. I've never seen something like that before. Okay, good. So it says the system reaches equilibrium at a temperature T. The Kc value is 9.4. First question, state Le Chatelier's principle. Let's first talk about Le Chatelier, and then I'll give you the proper definition. So Le Chatelier's principle says the following. What you do is you throw a whole bunch of stuff into a reaction container. Okay, so you'd throw the carbon and the sulfur into a container. You would let them react for a couple of hours until they reach equilibrium. You then come back to the system and you see, okay, it's at equilibrium. So once we are at equilibrium, then we can say, or then we can use Le Chatelier's principle. Le Chatelier's principle is all about at equilibrium. Okay, so this is not the answer, this is just my quick little explanation. So at equilibrium, if you disturb a system, okay, what does disturb mean? Disturb means change the concentration or pressure or temperature. Then system will be unhappy and will then try to oppose the change. Okay, so this is not the proper definition, this is just Kevin's little explanation. So once we are at equilibrium, okay, if you disturb the system, what does disturb means? It means you're changing something, you're changing the concentration of one of the substances, of a substance, or you change the pressure, or you change the temperature, then the system won't be very happy because it was at equilibrium. Equilibrium means it's nice and relaxed, it's at a steady state, and then suddenly you try to change something, so the system will be unhappy and it will try to oppose the change. So for example, if you increase the temperature, then the system will do whatever it needs to do to try and decrease the temperature. If you increase the concentration of carbon, the system will try to decrease the concentration of carbon. If you decrease the pressure, the system will try to increase the pressure. That's what it's all about. Now let me get you the proper word for word definition. So here it is here. When the equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that will cancel or oppose that disturbance. Okay, they change the wording from year to year. I haven't seen this kind of wording. I mean, I've never seen reinstate, okay? So you don't have to use that one. You can use whichever one you have been using throughout the year with your teachers or your textbook or whatever, okay? Okay, this question says, calculate the concentration of S at equilibrium. Alright, so I think let's go do a Kc table here. So, I've seen different learners like to do it in different ways, but I like to put the reaction, then the initial conditions, then the difference. Some learners would say the change, okay? I sometimes say different ones in my videos. Sometimes I use difference, sometimes I use change. I'm going to go with change in moles. This is initial moles. This is the reaction. This is the moles at equilibrium. And then this is the concentration at equilibrium. Okay, so the reaction is carbon goes, or plus 2s, goes to, let's just write this out nicely, goes to CS2. Right, now the initial moles, it says carbon reacts with sulfur according to the following balanced equation. The system reaches equilibrium at that. The Kc value is 9.4. Actually, I don't think we're going to be able to fill in much. All that we can fill in, oh, it says here, at equilibrium, we have 1 mole
of carbon disulfide. Okay, so this is going to be, okay, so what we know is that this one would originally have been 0. So that would have been 0 initially. And then the change would be a positive 1. They've just told us that, they told us this part. They told us the moles at equilibrium. Okay, so that means this would have to be a +1. Now, if you had to go work out, oh, they give us the volume over here. They say the volume is 2. So if you had to work out the concentration, you would use C equals to N over V, which would be its moles at equilibrium divided by the volume. So that's going to be 0.5. Okay. Now, for the change, this one would end up being -2 because the ratio here is 1 is to 2. And then this one will be -1 because it's 1 is to 1. These ones are negative because they are reactants. Okay? And then we don't know what they used. Sorry, it's not a 0. I was trying to circle. We don't know what these are. Okay, we don't know what that's going to be. And then the moles at equilibrium, we also don't know what that would be. And we also don't know what that would be. So you might think, okay, well, we're pretty stuck. But if you had to go calculate the Kc expression for this thing, remember, you only look at aqueous and gas. So that means this one will be eliminated from the Kc expression. So it's just going to be the concentration of CS2. Oh, what's going on? Concentration of CS2 divided by the concentration of sulfur to the power of 2. Because it has a 2 in the front there. Okay? Now, they've told us that the value of Kc is 9.4. And the CS2 is 0.5. And then this, we don't know. So I'm just going to say x to the power of 2. X to the power of 2. Okay? Let's just write that a bit better. And so, let me just write it better here, actually. We've got this. So I'm going to take the x2 over to the left. So we end up with 9.4 x2 equals to 0.5. I'm then going to divide by 9.4. I'm then going to take the square root of that. And so x would end up being 0.23. Now it's a concentration, so it's going to be mole per decimeter. They say here that the volume of the container is now doubled. After a while, a new equilibrium is established. Okay, so they were at an equilibrium position, and then the volume of the container was doubled. So now, after a few hours, you would need to have a brand new equilibrium. Now it says, how will the amount of S change as this new equilibrium is established? Choose from increases, decreases, or remains the same. Right, so let's try to figure this out. If you double a volume, okay, so let's say you've got molecules that are busy moving around in a container. There's 4 of them, for example. Okay, well, let's make it 6. Now, if you double the volume, okay, so you make it twice as big, you will still have the same amount of molecules in that container. Now, because they now have more space to move around, they are not going to collide with the container wall as often as they did over here. This means that the pressure exerted is going to be less. So when you double the volume, you actually halving the pressure. Or you could think of it as you decreasing the pressure. Now we said that Le Chatelier said, when a system is at equilibrium and a disturbance is made, which is either a change in a concentration, a pressure, or a temperature, then the system is unhappy and it will try to go against that. So what this person, whoever this was, when they came along and they just doubled the volume, they now caused the pressure in the container to be halved. So the system is not happy. The system's like, hey, why did you halve my pressure? Now I'm angry and I'm going to try to
increase my pressure now. You understand that, guys? Some of you get very confused with what disturbance was made and then how does the system respond. So the disturbance was that volume was doubled. Okay? Or you could think of it as the pressure was halved. They are inversely related. If pressure goes up, if volume goes up, pressure goes down. If volume goes down, pressure goes up. Volume was doubled. You can think of it as pressure was halved. So that was the disturbance. Now, we haven't even spoken about this next part. How will the system now respond? You understand that? So a disturbance is made. Now the system is going to try to fix it. How will the system try to fix it? It's going to try to increase the pressure. So system. This is not the answer to 6.4, by the way. I'm just making notes for you guys. System will try to increase the pressure. Now how does the system increase the pressure? If you've watched my videos on this before, you should be able to understand what we're about to do now. What we're going to do is we're going to look at this reaction and we're going to think about how can a system make the pressure in the container more? How does it do that? Some of you might be saying, oh, Kevin, could it maybe decrease the volume? And that's wrong. The system doesn't have the ability to suddenly make the container walls become smaller. Okay, that's impossible for the system to do. Maybe a human could do that, but not the system. The system is just all the molecules moving around. What the system can do to try and make more pressure is it could try to go either in this direction or in this direction, and it will do the one that makes more gas. Okay, so don't look at this part, that's not a gas. Look at this one and look at this one. On the right hand side we have 1, and on the left hand side we have 2. So if the system wants to make a more gaseous kind of scenario, it will end up going towards the left side where the ratio of gas is more. So this system that is unhappy is going to try to fix the disturbance by now going to the left hand side. So it says, how will the amount of S change as the new equilibrium is being established? Well, the amount of S is going to increase because the system is going to go to the left where these ones will become the products and this one will become the reactant. Okay, so we're just going to say increase over here. Now, this next question is what asks us to explain it for 3 marks. Okay, so first one, just tell them what was done. So volume, or let's actually no, we want to talk about pressure. So we say what made the system unhappy? We could say pressure was decreased by increasing the volume. That's what was done. That's the disturbance that made the system unhappy. Now, tell the examiner, what is the system going to do? System will try to increase the pressure by favoring the reaction. When I say that, I mean either the forward or the reverse, which will produce more gas. Okay, and then we can see that then we can just say that the reverse reaction will be favored. This question says, if the concentration of CS2 changes by X moles per decimeter. Now they're talking about after this new volume change that we have. The volume of the container is now doubled. Now it says, if the concentration of CS2 changes by X moles per decimeter cube, write down an expression for Kc in terms of X. Show all your workings, but you don't need to solve for X. Okay, so we need to quickly go back to this question over here in the very beginning, where we had
where we had these values here. Okay, this is important. I want us to go back to... Actually, I just want us to fill something in over here. So remember when we were doing this part of the question, what was the volume? The volume was 2 decimeters. So I just want us to quickly work out this value by just doing C equals to N over V. And if you say concentration multiplied by volume, you can get the moles. And so that's going to be 0.23 multiplied by the volume, which was 2 at that stage. And so that'll be 0.46, okay? We're not worrying about this because this carbon here is a solid. Okay, so what I'm going to quickly do now is just go copy these two down because they are going to be our starting conditions now when we go into question 6.5. I will explain this again now, but let's just go copy this all down. Okay, so you see what I've done. I've just gone and said moles at equilibrium before the volume was doubled. So remember in this question, they hadn't doubled the volume yet. So I just wanted to go see how many moles we had of those things. Then when question 6.3 came along, they did a doubling of the volume. Okay, and so now I'm just going to put a note here. Let's just say volume is now doubled, okay? And now we're going into the next part of the question. So, because these are how many moles of sulfur and CS2 we had, then the volume is going to be doubled. But can we agree that even though they're doubling the volume, the amount of moles in your container, that stays the same? The number of moles is actually telling you like the number of particles you have. Now, if you have a number of particles in a container, you double the volume, there's still the same amount of particles, right? The only thing that changes is concentration. If I say, hey bro, here's a glass of Oros, and then suddenly I'm like, you know what? I'm going to add a liter of water into that Oros. Would you agree that you still have the same amount of Oros in your container? You just have a whole lot more water, and so it's going to taste a lot less sweet, so the concentration has been decreased. But if you look at the original amount of Oros that was poured from the Oros bottle, that would be the same whether we added a little bit of water, half a glass of water, or 5 liters of water. It doesn't matter. The amount of Oros you had in that little glass is still the same. I'm talking about the Oros that comes out of the bottle before we add the water. That stays the same. Okay, what I want us to do now is I'm going to make a little bit of a modification to our normal KC table because they're telling us that the concentration changes by X. Oh wait, actually I just thought of something. We don't have to make a modification to the table. So we can now restart our table. So now initial moles. Now the initial moles is going to be these numbers over here because they are going to be, we're still going to have the same amount of moles from the previous equilibrium. Okay. Now we're going to go to our normal KC table. So change, and then, or this is normally change in moles, and then equilibrium moles, and then concentration at equilibrium. Okay, and right, so let's just quickly make some nice lines over here. Right, so what we can now do is, here, be careful here, they said that the change in concentration, so we know that we normally want to have change in moles, but that's okay, because what we can do is use the formula C equals to N over V, and we can just say change and change. It doesn't really matter. It makes no difference. Okay. So if the change in concentration is X for CS2, then we can work out the change in moles because the volume of the container. Now don't use a volume of 2 because they said that this was the original volume. So now the volume of the container is now doubled. Okay. So now we're going to use a bit of calculus to work out what is double that number over there. Okay, so we're going to take the first derivative. I'm just joking, guys. If we double this number, it becomes a 4. Okay, so there we go. Sorry if I gave you a mini heart attack there. And so if we now had to go and work out the change in moles, we're going to end up with 4.
X. Okay, so they said that the change in the concentration is going to change by X, so that means the moles is going to change by 4X. So I'm going to put a 4X over here, because that was for CS2, but then this one will be a 8X. But this one's going to be negative. Now, let me explain everything. So, we know from the ratios normally that this is in a 1 to 2. So that's why if this one's a 4, then this one's an 8. Now, Kev, why, my bro, is this one a negative, and why are you keeping this one a positive? Good question. So, we know that from question 6 where was it? From 6.3, we said, how would the amount of S change as the new equilibrium is being established? Well, we found out that from Le Chatelier's principle, this direction is going to be favored. Okay. So that direction is going to be favored. So the amount of this stuff is going to go up, and the amount of this stuff is going to go down. And that's why I'm making this one a negative and this one a positive, when normally it's the other way around. Okay, now the rest is easy. We can go fill everything in. So this part we just say 1 minus 4x, and then this part will be 0.46 plus 8x. And then concentration at equilibrium, we can now just say C equals to N over V. And we know that the concentration, the volume is 4. Don't use a 2, it's a 4 because we doubled. That was the original volume. And then here we're going to say 0.46 plus 8x over 4. So this is something I have seen them do quite a few times in exams. It's not that common, but it can happen. I've seen it like maybe 3 times in all the years I've been teaching. It's where they have an original equilibrium, and then they do another change, and so the information from the original equilibrium becomes the starting position of the new change of equilibrium. Okay, so you see how we had to carry that over to the new part. Okay, but we're not done. Now they want us to go get Kc, so we know that Kc is... Now, here's this part confuses some learners. They think, because the reaction is going in this direction, this will be the products, and this will be the reactants, and then they want to put the products over here. But that's not correct. The way Kc works is you always put the right-hand side over the left-hand side. Always. Whether we're going reverse or forward makes no difference. So you're going to put the CS2 concentration. And then at the bottom here, we're going to use the sulfur concentration to the power of 2, because there's a 2 there. I'm not using the carbon because Kc only looks at gas and aqueous. And so now we can go fill this in as Kc is equal to 1 minus 4x over 4. Oh no, there's no 2 there. And then divided by 0.46 plus 8x over 4 to the power of 2. And then the memo does something quite weird. I would have left it like that because they just said, where did they say it here? Write down an expression for Kc. So I would have just said Kc is equal to that. But they went and filled in the original Kc value of 9.4. I will explain that part now, which I did find a bit weird because they just wanted an expression for Kc. But they did tell us that Kc is 9.4. Now, some of you might be like, yeah, but Kev, my bro, wouldn't the Kc value be different because we are at a new equilibrium? And that would be a negative, sir. The reason is Kc only changes with temperature. Now, when they went from the first equilibrium to the second equilibrium, what was the change? It was a volume change. So when you do a volume change or a concentration change, Kc doesn't change. So we can keep it as 9.4. So if they ever asked you to calculate X, you would have needed to know that, okay? It is only temperature. Write this on your forehead, or write it on your friend's forehead so you can at least see it when you're in your test. Kc only changes with temperature. So here's the last part of the super long question. So it says, the reaction rate time graph below represents further changes that are made to the mixture. The volume
the volume of the container is kept constant. First question, what do the parallel lines between TA and TB mean? Well, when you have parallel lines, it means the system is at equilibrium. So system at equilibrium. So with this question it says, what change was made to the equilibrium mixture at T time B? Okay, so here we have a rate graph and we can see that there is a spike, but only one of the reactions is spiking, okay? So remember what we've learned is that if only one of the reactions spike, then it's a concentration change. If both spike, but one spikes more, then it could be pressure or temperature. When I say spikes, but one spikes more, I'm talking about something like that, where you can see both of them are spiking, but you can see that one's got a little spike and this one's got a spike, but they're not equal in spike. Okay? Then what we've learned is that if both spike exactly the same, then it's a catalyst. For example, if you have something like this. Okay, let me make that a bit better. If you have something like that where they spike equally, then it's a catalyst. Okay, so what we can see is at time B is that we have this scenario here where only one of the reactions spike. You can see the spike is this part over here. Okay, then it is a concentration change. But now we can't just say concentration was changed. We will have to say which substance's concentration was changed. So what we can see is that the forward reaction is the one that is spiking. So that's the one that is, in this scenario, that means that that one is favored. Let me just explain that part carefully. When we look at this reaction rate diagram, we can see that the original rate is over here, and after the new equilibrium, it's over here. So can we agree that there has been an overall increase in the rate of the reaction? Now remember that thing I've told you that when we can see, okay, but now we can't just say that it's a concentration change. We need to be able to specify which substance was changed. So the way that we can do that is we need to try figure out, what we can see is that the overall reaction rate has increased. Can you see that the equilibrium position here is at a lower rate than it is over here? So we are now at a higher reaction rate. So what has happened to the overall rate of this whole system? It has increased. Okay, so the overall reaction rate, talking about the forward and reverse, overall the reaction rate has increased. Okay, now we've got to try to figure out, remember that thing I told you, that little rule I've told you guys before? Let me write it down for you here. What we used to say was, if the overall rate increases, then spike the favored reaction. Remember that? And then we said, if the overall rate decreases, then spike the non-favored reaction. So the reaction that was not favored. So we've just seen now that the overall rate of reaction is increasing. Okay, so we're going to use this. So it says here, if the overall rate increases, which we know it did from here, it says spike the favored reaction. So can you see which reaction was favored? Look at this one. That's the one that's spiking. So the forward reaction was favored. So that means that whatever was done to the system caused
the forward reaction to be favored. Now, remember, we can't change the concentration of a solid, okay? We will not look at that. We will only look at gaseous and aqueous. So, the only way that the forward reaction would be favored would be to increase the amount of this. Some of you might be saying, yeah, but Kevin, couldn't we also decrease the amount of this? Okay, so that would cause the forward reaction to be favored. You are right about that. But if you decrease the concentration of one of these substances, then the overall rate of the system would actually go down. It would have spiked downwards instead, and it wouldn't have spiked upwards, okay? So it can't be that one. So it's going to be the concentration of sulfur was increased. So we can just write our answer here. Concentration of sulfur was increased. It's only for 1 mark. Okay, let's move on to this one now. So it says, give a reason for the sudden change in the reaction rate at TC. Okay, so at TC we can see that there is a spike. But if you look carefully, they're both spiking. Can you see this one also has a little spike over there? See that? So what we've learned, remember, and I wrote it over here now, is that if both of them spike, but they don't spike the same, then it could be a pressure change, which is due to a volume change actually, or a temperature. But they told us here that the volume of the container is kept constant, so it can only be a temperature change. So we're going to say that the temperature was changed, but we need to know if it was increased or decreased. That you don't use this part for. What you do is you just look at the overall rate. So if you look at the rate over there, and then if you look at the rate afterwards, we can see that the overall rate has decreased. And so what that means is that the temperature was decreased. Okay, now for 6.6.4, it's a bit of a weird question because they want us to explain it, but they want us to explain for 3 marks. So, literally, if you decrease the temperature, then the overall reaction rate is going to decrease. But what they're actually wanting us to explain, they just haven't worded it properly, and that's why it's worth a bit more, is why does it decrease in this way? Why does the forward reaction spike lower? Why does that one spike like that? And what temperature, and why... Yeah, so they're pretty much wanting us to explain a bit more about like why it spikes the way it does. Because they just said, give a reason for the sudden change. We just said temperature was decreased for 1 mark. Then it says fully explain the answer. I would have just said that the overall reaction rate has decreased. That's why we said the temperature has decreased. But they want us to go into a little bit more detail now. So now we probably are going to have to use this part over here. So what we can say is that the temperature was decreased. Okay, that's the disturbance that we said for 6.6.3. So what would the system try to do? The system will try to increase the temperature. How does the system increase the temperature? By creating heat. That means by going exothermic, by favoring the exothermic reaction. Now, some learners get a bit confused. I've seen it in the comments. They think, oh, the temperature was decreased, so that means endothermic. Because when you go endothermic, it decreases the temperature. But this part here has nothing to do with endothermic, exothermic. This part here. This part here is simply what change was made to the system. Like maybe there was some person who suddenly put a whole bunch of ice into the container, or maybe they lowered the temperature of the room or something like that, okay? So this has nothing to do with exothermic, endothermic. When the system now is unhappy and the system is now going to try and correct the change that was made, that's where we then start looking at exothermic, endothermic. That's where the system now tries to correct the change that was made, okay? So that is why, so now the system is going to try increase the temperature. How does it do that? By favoring the exothermic reaction. Now, if you look over here, they're giving us this symbol over here. Remember that this symbol is always whatever they put over here. They could either do it like that, or they could put a negative. Whatever they put over here is always the forward. That's always for the forward reaction. So does that mean that the forward reaction is always going to have this symbol? That's what some students get confused with. No, it doesn't mean that. It could be this or this. But what I'm saying is that whatever symbol they do put over here, that will be for the forward reaction. But every reaction is different, so they can use a different symbol over here. Okay? So this means endothermic. This means endothermic. So therefore, what we can say is that the forward reaction is endothermic. And when the reverse reaction gets favored, well, then that would be exothermic. So some students think, okay, so when the temperature is decreased, that means endothermic. So was the forward reaction favored? No, not at all. This part here has nothing to do with forward and reverse. That part there is just the disturbance that the person or someone has made. It is this part here, the way that the system now reacts to that disturbance. That's where we start looking at forward, reverse, endothermic, exothermic. Okay? So, the system will try to increase the temperature by favoring the exothermic. So that means reverse. Therefore, the reverse reaction will be favored. Now, remember that rule once again that we've spoken about. I'm going to write it down again for you. We wrote it here earlier. When the overall rate increases, the favored, not forward, I'm not saying forward, I'm saying the favored or the chosen, the favored reaction is spiked. When the overall reaction rate decreases, the non-favored reaction is spiked. Okay, so what we can see here is that the overall, over here, from here to here, the overall reaction rate has decreased. So this means we are looking at this part now. So the non-favored reaction is spiked. So which reaction was favored? It said, therefore, the reverse reaction is favored. So the reverse reaction was favored. So that means the forward reaction should be spiked. Let's see if that's what happened. Forward reaction is the solid line. Can you see that that's the one that spiked the most? I should say, yes, spiked the most. And spiked the most, because they both spike when it's a pressure or temperature change. Okay, so we can see that the forward reaction was the one that was not favored, so that one will spike down the most. So we can just say here that the forward reaction will decrease the most. Ethanoic acid is a weak acid that reacts with water according to the following equation over here. So that's just a normal ionization where you've got ethanoic acid plus water. You can see that it donates its hydrogen to the water. So the water ends up becoming H3O, and then you can see that this hydrogen has been removed when you look at it over here. Okay, so all that's happening is that this hydrogen is being transferred to this water molecule, so it then becomes H3O. Okay, so the first question, define an acid using the Bronsted or the Lowry-Bronsted method. Okay, so remember what we've spoken about before. We've spoken about acids, and we've spoken about bases, and we've spoken about Arrhenius definitions and Bronsted definitions. Okay, so we might as well just go through all of them now for revision purposes. So, with an Arrhenius, this guy was obsessed with water, okay? So what this person said was that an Arrhenius acid produces
H3O when in water. Okay, and Arrhenius, let's just see what he said for bases. He said that an Arrhenius base produces OH minus when in water. Bronsted is a little bit more of a cool dude, and he adapted the definitions to be a bit more easy to work with. Okay, this guy just said that an acid is a proton donor and a base is a proton acceptor. We don't need water or anything like that, so we can just say it is a proton donor. It gives away protons. Okay, this question says, give a reason why ethanoic acid is classified as weak. Remember that if something is strong, then it loves to ionize. If it's a strong acid I'm talking about. Strong acids, what do acids do? They give away protons. So if it's a strong acid, it means that it's really strong or really good at doing that, giving away protons. If it's a weak acid, then it's not very good at giving away protons. So give a reason why it's classified as weak. We can say that it does not. We can say it does not ionize completely. You might say that it ionizes partially, okay? You might even say that it has a low Ka value. If you're comfortable with Ka, Kb values, you could even say that. This question says, write down the formula of the two bases in the equation above. Okay, so obviously if we go this way, you get a base, and if you go this way, you get a base. So what do bases do? Bases are proton acceptors, okay? So you can see that if we go this way, who's accepting the proton? Well, it's this one. You can see that the H is being given to this one. So this one is accepting it. So we can say H2O and then just put the liquid over there. And then if we had to go this way now, who's accepting the hydrogen? Well, if you go this way, you can see that this H, one of these H's, is going to be given back to this one over here so that it can go back and become this. So this is going to be the base in the reverse reaction. So we can just put here CH3COO minus aqueous. A flask contains 300 centimeter cube of dilute sodium hydroxide of this concentration. First question says calculate the number of moles. Okay, that's a nice easy one because we can just use C equals to N over V. And so the concentration is 0.167. Volume, be careful. This is in decimeters. This is in centimeters. So we need to convert the centimeters to decimeters. And to do that, you divide with 1000. So this will actually be 0.3. Now, if you had to work this out, you would have to multiply like that. And this will give us 0.05 moles. 0.05 mole. Where can we write that? 0.05. Ethanoic acid of volume 500 centimeter cube. Okay, let's first draw a picture of what we have so far. What we have so far is we have a container filled with NaOH, and it's 300 centimeters cubed and a concentration of 0.167. Okay, now it says ethanoic acid with a volume of 500 and an unknown concentration is now added to the flask to make 800. That makes sense because 500 plus 300 is 800. So there's no rocket science there. Okay, so we're going to take some ethanoic acid, which is CH3COOH, like we see over there. And this one is 500 centimeters cubed, but X for the concentration. Okay, and they're going to add these two together into one flask. So if you want, we could actually go and draw it out as one big flask, which is 300 centimeter cube of the NaOH and then 500 centimeter cube of the CH3COOH. Okay, so they're just adding those two together to make that over there. Right, now it says, it is found that the pH of the mixture is 11.4.
the balanced equation. There we go. First question. Calculate the concentration of the OH minus in the mixture. Okay, so that's quite an easy one because we know that pH is equal to negative log of H3O plus concentration. Okay, so we could say that the pH is 11.4. So we could say 11.4 equals to negative log of the H3O plus. And I'll show you a second way to do this. Some learners like to use this formula, pH plus P of OH equals 14. I'll show you that method as well. Okay, so, but now I'm just using a different method. Right now I'm using the KW method. Okay, so we could then say that, okay, so we've got, I'm going to take the negative to the left. So we're going to say negative 11.4 equals to the log of H3O plus. Now remember that there's actually a 10 over there because it's a standard log. So you got to remember how to get this by itself. So you're going to say this number to the power of this number. So 10 to the negative 11.4 equals to this. Okay. And so if you had to go work that out, you end up with 3.98 times 10 to the negative 12. And that's a concentration, so it's moles per decimeter. Then you could use the KW formula. Do they tell us what temperature we are at? Okay, so technically they have made a bit of a mistake here. They should tell us that we are at 25 degrees because we know that at 25 degrees we've got a KW formula that is equal to this. But then I went and looked on their memo and they did use this formula anyways, okay? So it's not like we had to use something different, but they should have told us at 25 degrees. Because this formula at 25 degrees is equal to 10 to the negative 14. Okay, so we know this value now. We've just calculated that, so we can then go and do this multiplied by 3.98 times 10 to the negative 12 equals to 10 to the negative 14. So then you could get the OH minus by itself by just dividing this on the other side. After you do that, you should end up with 2.51 times 10 to the negative 3, and that's going to be in mole per decimeter. Okay, if you prefer this formula here, let me show you how that would. This one actually works quite nicely, I won't lie. Let's quickly talk about that one. Oh wait, the first part all stays the same. Oh no, it doesn't. I lie. Sorry, what we'll do is we'll do the following. Okay, let's just write this answer down here. Okay, mole per decimeter. Okay, method 2. Method number 2. So if you what you can then do is you could say, okay, the pH is 11.4. Now there is a formula that goes pH plus P of OH is equal to, and that is always equal to 14. Now if we know that the pH is 11.4, then we can say 11.4 equals to plus POH equals to 14. You could then solve for POH and you should end up with 2.6. Okay, so 2.6. And then you can just say, okay, so if we know that there's this formula, pH is equal to negative log of H3O plus, well then POH is equal to negative log of OH minus. And so we know this value is 2.6. And then there's a little 10 here. And then you can just do what we did earlier, where you could then say negative 2.6 equals to log 10 of OH minus. And so OH minus concentration will be 10 to the negative 2.6. And so that would end up giving you, let's rather write it over here. Yep, same answer. 2.51 times 10 to the negative 3 mole per decimeter. Okay, so it's going to be 2.51 times 10 to the negative 3 mole per decimeter. This question over here says, calculate the initial concentration of the ethanoic acid solution. Okay, let's have a bit of a chat. So what we've spoken about before is when you add an acid and a base together. Okay, so if you add equal, okay, so I have showed this before, but let's go do it again. So 1, 2. So in scenario 1, you add equal stoichiometric amounts. So you add just the right amount of each type, okay? So graphically that could look something like this. You add the perfect amount of acid and the perfect amount of base. Now remember, when you add an acid and a base together, they fight each other and they neutralize each other. And so if you add just the right amount stoichiometrically of each one, then at the end, there will be no acid or base left over. So no acid or base left over. And so therefore, pH will be 7. It'll be a perfectly neutral scenario. In situation number 2, let's say you add more acid than base. And remember, I'm talking about stoichiometrically. What that means is that I'm looking at the ratios from the balanced equation as well. And even after looking at those ratios, if we have added more acid than base, then, okay, so let me try to explain what I mean. So let's say you have a reaction where HCl, or let's say we've got, I'll make up my own reaction. 2A for acid plus B gives us C plus D, okay? So let's say this is a reaction. So the reaction tells us that you need twice as much acid than base. So if you add twice as much acid than base, and that then this reaction would actually work out perfectly, and you would have no acid or base left over. That is actually what it would look like over here. You're adding a perfect stoichiometric amount. This is the stoichiometric amounts, okay? So let's say we have this reaction, but let's say I add 5 parts acid and only 1 part base. So can you see that I am exceeding the stoichiometric ratio? So in this kind of scenario, you would have more acid left over. Okay, so your reaction container would look something like this. You would have a lot of acid and you would have a very small amount of base. So then at the end, you would have acid left over. Acid will remain after the reaction. Some of the acid will be used up when it reacts with the base, but after they have been reacted with each other, there will be some acid will remain after the reaction. And so that acid, let's quickly make a note here. The leftover acid will ionize with water. And what does that do to the pH? It makes it become less than 7. Okay, and then in situation number 3, if you have more... Why is my computer lagging like that? Yo, Kevin, you need more RAM, my bro. So, so if you have more, more base than acid, shame Kevin's using a 512 megabyte RAM, my bro. This guy needs an 8 gig. So, okay, I don't really have 512 megs, for those of you that are laughing at me right now. It's a bit better than that. Okay, so more base than acid. Then what you would have is a situation that looks like this. You've got lots of base, and then a little bit of acid. So then you'll have base will remain after the reaction. So then what do bases do? They dissociate. So base will dissociate, or let's say leftover base. The leftover base will dissociate, and what does that do? The pH will then become larger than 7. Okay, so those are the 3 scenarios that we have. This one here is also a titration. When you do a titration, we don't have any leftovers, okay? But this question that we're busy with here is not a titration. Here they're just taking a whole bunch of this and a whole bunch of that, putting it together, they're letting them react, and then at the end, we know that one of them is left over because look at the pH. The pH at the end is 11.4. So immediately, we don't even have to go work out which one was the limiting reactant. Why? Because look at the pH. It's 11.4. That is very basic. What that means is that here we had the sodium hydroxide, so we had the sodium hydroxide, and then we had acid. We put them together, and after they reacted, we've got a pH of 11.4. That means that the sodium hydroxide was in excess, and so that's the one that is left over. So check this out. In 7.2.2, or let me try to think how I want to present this quickly. Hold on. Okay, so what I think we can do is, remember that this is when we added them together, but now let's quickly see what it looks like after the reaction. So after the reaction, after both of them, after both the acid and the base have reacted, we're still going to have 800 centimeters cubed. Now that part there confuses some learners. They think, whoa, Mr. Kev, if these two have just reacted with each other and you said that this one is left over, then won't we take away the 500 because that's gone? But what we need to understand is that most of chemistry, or all chemistry around us, is actually taking place in water. So what this actually is 300 centimeters cubed, pretty much of water, by the way, with a whole bunch of NaOH molecules floating inside of it. Chemistry is all about water. If we look at this one, it's actually going to be approximately 500 centimeter cube of water with a whole bunch of CH3COO molecules floating inside of it. So when the NaOH and the CH3COOH are reacting, we have now removed all of the CH3COOH, but the volume of 500 remains because that was pretty much water anyways. So we still have 800 centimeter cube of water floating around, and the concentration of the OH minus, which is the leftover stuff, is 2.51 times 10 to the negative 3, and that is the OH minus concentration. Okay. Now, where did that OH minus come from? That OH minus came from, what did we say on the slide over here? We said that if you have more base than acid, which is the scenario we have now, it says that the pH will be larger than 7, which is what we got, and it says that the base will dissociate. So that base is the NaOH. So that NaOH, what happened is that it dissociated after these two things reacted. The leftover NaOH dissociated into Na plus and OH minus. Hello, look at that. So then make sure that this reaction is balanced. Yes, it is. So what we can now do is we can say, okay, we can work out, we can take these two values and we can work out the moles of OH minus. That'll then allow us to work out the moles of NaOH that was left over after these two things reacted, right? You guys are going to see how we're going to do this now. So we can go work out the moles of of OH by saying C equals to N over V, and then N is equal to CV, okay? So the number of moles would be its concentration, which is 2.51 times 10 to the minus 3, multiplied by this, but it must be in decimeters, like that. And that'll give us, I'm going to round off to 2.01 times 10 to the minus 3. But you don't have to round off. In the memo, there is a range that they're going to give us. I'll tell you what that is once we finished at our final answer. Okay, so now you got to think carefully here. So this is the moles of OH minus floating in this container. Okay, so then if we can just look at the ratio here, can you see that it's in a 1-to-1 ratio? 1 is to 1. So therefore, the moles of NaOH is also 2.01 times 10 to the minus 3. Where is that moles? That is the moles of NaOH in this part over here, which is the leftovers after these two things have already reacted. So what we can then do is come all the way back up to here, or actually this question, and we can see how many moles of NaOH we had in the very beginning, which was over here. And how many moles was that? 0.05. So we had 0.05 mole of NaOH over here. Then at the very end, after the reaction with the CH3 has taken place, how much NaOH do we have? This amount over here. So then, would you agree with me that if I minus these two values, it'll tell me how much NaOH reacted in the reaction with the CH3COOH. Let me explain that again. In the very beginning, before any reaction took place, we have this much NaOH. At the very end, after the reactions have taken place between these two, we still have leftover NaOH, and it's that much over there. So where did the missing amount go? Well, it must have reacted when these two were busy reacting over here. So we can say, therefore, the moles of NaOH reacted must be 0.05 minus 2.01 times 10 to the minus 3, which would then give us 0.048 moles. So I know then that in this reaction, the amount of NaOH that reacted was 0.048 moles. If I then know that this is a balanced reaction, and it is, and I double checked it, I can see the ratio here is 1 to 1. Then I can work out how much moles of CH3COOH must have been in this container. Because I know that all of the CH3COO reacted, so however much I get here is the same as the amount here. Okay, so therefore it's a 1 to 1 ratio, so I can say 0.048 mole of CH3COOH. Okay, and then I can work out the original concentration of the CH3COOH, because I know how many moles it has and I know what its volume is, and so I can then just say C equals to N over V, which is equal to 0.048 over 0.5 because it's decimeters, and that'll give 0.096, and that's moles. Concentration, yeah, mole per decimeter. Now, the range of answers that you're allowed to get is 0.095 up to 0.1. Okay? A piece of zinc is placed in a test tube containing acidified permanganate solution. After some time, it is found that a redox reaction has taken place. Using the table of standard reduction potentials, which I will go and fetch for us now, to answer the following questions. Okay, let's go get the table. So here on the table, I know it's not the biggest of tables, but let me just quickly show you. By the way, I'm using table 4B. Some of you like to use 4A. All that I would do now, and by the way, this is table 4B, okay? So all that I would do now is just go find the Zn. Now, here's Zn, but you're not going to highlight the Zn2+. They specifically said zinc, not Zn2+. So there it is. And then I'd go find MnO4-, which is over there. Fantastic. Then they said that a reaction does take place. Perfect. So I'll literally make it react. So this will just go this way, and this will just go that way. Easy as that. Okay, so that's what's going to happen. Let me just try to do it so we don't get in the way here. And there. That's what's going to happen. Now, just so we can quickly see the question, it says write down the name or formula of the reducing agent. Okay, so a reducing agent, if you just look here, this one says increasing strength of oxidizing agents. So that means all the oxidizing agents are here on the left-hand side. And then this right-hand side arrow says increasing strength of reducing agent. So the reducing agents are these ones on the right-hand side. So it's going to be zinc. So it says the name, so you could say zinc, or the formula. Don't say Zn2+, because that's this side. Okay. Next one says, refer to the relative strengths of the oxidizing agents to explain why a redox reaction has taken place. Okay, so they said using the oxidizing agents to explain why a reaction has taken place. Okay, so they want you to then use the oxidizing agents, which is this one over here. So you're just going to say MnO4 is a stronger oxidizing agent than, and then just go up to the other reaction and then choose this one, because that's the one it would have been if this one wasn't the winner. Okay, so you just compare it to that one over there. So you say MnO4 is a stronger oxidizing agent than Zn2+, and will therefore oxidize, because it's an oxidizing agent, it'll oxidize the Zn to become Zn2+, to Zn2+. Done. A standard electrochemical cell is shown below. Sorry, this just says below. Write down the function of component Y. So component Y is a salt bridge, and what it does is it separates the 2 half cells. Another one you can say is it maintains electrical neutrality. You can choose any of those. Sorry, that's just an A. Or you could even say, completes the circuit. Okay, this one, that one's done. This one says, in which direction will electrons flow in the external? Choose from Ni to Mn or Mn to Ni. Okay, so we've got to try to figure out which way it's going to go. So we need to go look at our table. Okay, so step 1, go find the 2 reactions on your table. So the Ni reaction is over here. And then the Mn, where are you? Mn, there. Okay, now, I'm using table 4b, and so if you've watched any of my videos, you would know that this is a galvanic cell. It happens spontaneously. So the only way it can happen spontaneously is if we look at the arrows. So you see that arrows going up, and you see that arrows going down. So choose the one on the left side, that is the lower, so that's going to be this one. And then on the right-hand side, choose the one that's higher up, so that would be that one. And so that is how the reaction is going to go. So that means this one is going to go in that direction, and that one is going to go in that direction. So let's try to figure this out now. So it tells us that the Ni is going to have a reduction reaction. So it's going to go Ni2 plus 2 electrons gives us Ni. I'm just copying that. And then this one is going to go the other way. So this one's going to go Mn turns into Mn2 plus 2 electrons. So can you see that on this side, it's going to use up 2 electrons. And then on this side, it's going to give away 2 electrons. So what it means is, let's start over here. It tells us that the Mn is going to turn into Mn2+, and then there's going to be 2 electrons given away. So those 2 electrons are going to flow upwards like this, and then they're going to be absorbed over here in this reaction, because you can see that the Ni2+ is going to add 2 electrons to itself to become Ni. So the electrons are going to go in this direction. Okay, so we are going to say from Mn to Ni. Next question says, calculate the initial EMF. Now, EMF is a formula on your formula sheet. It's the cathode minus the anode. Now, cathode is always the place where reduction happens, and then anode is always the place where oxidation happens. So you should know by now that a reaction that's written from left to right like this is a reduction reaction, and a reaction that's written from right to left like this is a oxidation. So your EMF is equal to the reduction value. So the reduction value is negative 0.27 minus your oxidation value, which is negative 1.18. So you're just going to say negative 1.18. And if you calculate this, you end up with 0.91 volts. Okay, this next question says, write down the balanced equation for the net cell reaction. Okay, easy. So we've already got this one and we've already got this one. I'm just going to write them underneath each other. And then here we've got Mn turning into Mn2 plus 2 electrons. Okay, now to balance them, we always want to make sure that these are the same. Luckily they are in this case. So we can just go put everything together now. So you see there's an arrow and an arrow. So everything on the left of the arrow will go together. So that'll be Ni2 plus 2 electrons plus Mn. Now we're going to put everything on the right hand side of the arrow. So Ni plus Mn2 plus 2 electrons. Now the electrons are the same, so we actually get rid of those. And so there's your answer. That is your overall reaction. So next one says, the concentration of the Ni2+ is increased. How will this affect the voltmeter? It's very easy what you do here. You literally use your knowledge of equilibrium and Le Chatelier. So if this concentration is increased, then what will happen? The system will try to decrease that. How will it decrease this? Well, it'll do that by favoring the forward reaction. So when the forward reaction is favored, the voltage goes up. Voltage goes up. When the reverse is favored, then the voltage goes down. Okay, so what will happen to the voltage? It will increase. The diagram below represents a simplified cell using the electrolysis of concentrated chromium chloride. Electrolytes R and T are made of carbon. Okay, the net cell, I just want to quickly see something here. The diagram below represents electrons of concentrated. Okay, that's a key word. Hey, I actually just read over that without thinking about it. Remember, they sometimes use, remember in my sections we have spoken about electrolysis of aqueous solutions? Okay, let me quickly give you a summary. In our lessons, we have spoken about electrolysis, and within that we've done molten, and we've done aqueous. Within aqueous, we've made some good points about dilute and concentrated. Okay, and if you've watched those lessons, then you would know what to look out for in this lesson. Okay, or this video, this exam question. So the first question says, define the term electrolysis. No, I'm just joking. Define the term electrolysis. So it is the use of electrical energy to produce a chemical change. Okay. Now, this next one says, the graph below, not drawn to scale, represents the changes in the mass of electrode T during electrolysis. Okay, so electrode T, we can see that its mass is increasing. Okay, that's a hint right there. A current of 2.5 amps passes through the cell for 10 hours. Calculate the total charge that flows through the cell. Okay, so from grade 10, we know that there is this formula I equals to Q over T. They actually do give that to us on the formula sheet, but on the formula sheet they actually use it in the other way around. They put the Q first, and they use a small q, which is interesting. But it's the same thing. At least that'll give you an idea of there's your formula. So they said calculate the total charge. So that'll be equal to the current multiplied by the time, but the time must be in seconds. So you're going to say 10 multiplied by 60 to convert it into minutes, and then multiplied by 60 to convert it into seconds. And that'll give us 90,000 coulombs. The next one says, calculate the value of X as shown on the graph. Okay, so it's a brilliant question, this one. Quite a bit of a challenge, but let's have a look. So, yeah, they used to ask us in the IEB quite a lot, and they never really used to ask it in the CAPS papers, but now I'm starting to see it quite often, these ones that talk about current and charge. It's fairly new to the CAPS question papers. Okay, so all that I want you to do is look at this over here and just try to break it up into two reactions that you can see on your table 4A or 4B, whichever one you use. Okay, so I want you to go find everything on this table now that has things that you see here. So for example, a reaction that has CR. So there's one over here, but then there's also one over there. We won't take this one because this one has a CR2 plus and a CR3 plus, but it doesn't have a CR. Okay. Then we're going to go find all reactions that have like a Cl2, for example, and that would be this one over here. Okay. So we definitely, for the Cl part, we are definitely sorted. We have this reaction down here. Now, for the CR, we have a little bit of an issue because there's two CRs, okay? Now, from grade 11 valencies and things like that, if you look on your periodic table, Cl has a valency of -1, okay? But there's 3 of them, so you could think of it as -3. So then if this molecule here is neutral, then this Cr would have to be a +3 so that it cancels out. So we're looking for the Cr that has a +3, and that's going to be this one then, okay? So we don't want this one. So the two reactions that we will consider will be Cr3 plus 3 electrons giving us Cr, and then the other one we will consider is Cl2 plus 2 electrons giving us 2 Cl minus. Now, if you look carefully, they told us that the mass of electrode T is going to increase. The only way that that can happen is because the solid is going to be deposited on that. On the other electrode, we're producing Cl2, but Cl2 is a gas, and that gas would bubble away. It would just bubble into the environment, but it wouldn't collect on R. So because they're telling us that the T electrode is increasing in mass, we can see that over here, that means that this is where the reaction Cr3 plus 3 electrons turns into Cr is happening. Okay, now what we're going to do is we know that there are electrons that are moving through this battery. There's electrons, okay, or moving through this circuit. So what we'll do is we know that there's a total of 90,000 coulombs of charge. So we can use this formula, N equals to Q over QE. But be careful. Normally N means moles, but in this formula N actually means the number of electrons. So we know that the total charge transferred is 90,000. The charge of an electron is 1.6 times 10 to the minus 19. Technically the charge of an electron is negative, but when we're just trying to work out the number of electrons, you can just leave out the negative. Okay, they even do that on the memos. And so if we work this out, we end up with 5.63 times 10 to the 23 electrons. Okay, now check this out. We know that if you look at this reaction, the ratio of electrons to the amount of chromium that has been, or let me just first, so we know that the amount of electrons that have been now transferred over is this many electrons, okay? Now, the reaction tells us that for every 3 electrons, there is 1 mole of chromium. Okay, or for every 3 electrons, there's going to be one. For every 3 electrons, there will be 1 chromium electron, or for every 3 moles, there will be 1 mole. Okay, whichever ratio you want to look at. So if we then say that the ratio of electrons to chromium is in a 3:1, then if we have 5.63 times 10 to the 23 electrons, then we could then work out not the moles, this isn't moles, this is the number of electrons. So we could then use cross multiplication. So we could say 3x equals to 1 multiplied by 5.63. So say multiply by 5.63 times 10 to the 23. And so x would end up being 5.63 times 10 to the 23 divided by 3. And that'll give us 1.88 times 10 to the 23 Cr atoms. Okay, now we can now use Avogadro's number, which tells us that to work out the number of moles, we can take the number of atoms or molecules divided by Avogadro's constant, which is then going to be 1.88 times 10 to the 23 Cr atoms divided by Avogadro's constant, which is that number over there, which is then going to give us 0.31 mole of chromium. And now we can work out the total mass of chromium by using N equals to M over capital M, which is then going to be 0.31 equals to the mass divided by chromium's molar mass. If you look on the formula sheet, it's not the formula sheet but the periodic table, it's 52. And so if you then had to go work out the mass of, chromium, you would end up with 16.12, but that's not the final answer because the question says what is the value of X. So this mass of this electrode was already 2.2 grams at the beginning, and during the process of moving electrons over, we processed, or we deposited 16.12 grams on top of that electrode. So you have to add the 2.2 grams to that, and you should end up with a final answer of 18.32 grams. Okay, now the range of answer you're allowed to get is anywhere between 18.32 up to 18.40. So in summary, what we're doing is we are calculating how much charge moved over. From that, we can calculate how many electrons. Then from this equation, we can use the ratio to work out the mass of chromium. And then we can simply just convert that back down to a mass of chromium.